Okay, so we can start. So I would like to welcome everybody for the second day of our summer school. And today we will have four very interesting lectures in the scope of our summer school. So the first lecture will be held by Niccolò Bartoloni from Unify, and the title is Precision Viticulture, State of the Art and Future Perspectives. Please, Niccolò, the floor is yours.
Okay, thank you so much for everybody. As I said, Natasha, Niccolò Bartoloni, I'm an agronomist, and today we are going to talk about tools for precision and digital agriculture. Do you hear me well? Do you see everything?
Yes.
Perfect, I can start. So, precision viticulture is based on the integrated use of digital technologies, geospatial data, and advanced monitoring system to collect data information about managed vineyards. The goal is to adopt highly specific agronomic practices to which allow the intervention to be adapted to every single corner of the vineyard. In this lesson, we are going to talk about common technologies used in precision viticulture include ground air sensors, GPS, drones, satellites, advanced software that analyze the data collected and provides winemakers with useful information to optimize irrigation, fertilization, phytosanitary treatments, and harvest. Everything you are going to see in my presentation is now used by some wineries. So if there is anything about research or something have to be adapted in the vineyard. So I'm going to see real cases. Okay. The advantage of using precision agriculture in viticulture is to optimize resources as water, fertilizers, pesticides, improve grape quality by monitoring the health of the vineyard in real time, and environmental sustainability. So we can reduce the use of pesticide fertilizers and waters, contributing to more sustainable agriculture with a lower environmental impact, and also to respond to climate change. But I know that in the late morning there is another colleague that is going to talk about it, so I'm going to fix or talk anything about climate change. So the instruments we can divide in control tools that measure what is happening on the ground, forecasting tools that estimate what's happening, decision and prescription tool, they are the DSS, so support data-driven decision making, and a quotation system. So we are going to see all this morning. I'm going to be brief. Let's see if I can finish at half past 10. So we have satellites, drones, or proximal data from instruments, field observation with, for example, mobile app, soil analysis, weather station, and hill maps or prescription maps. Okay, if you take some data, we can do it with a quad, with a drone, with an aerial or a satellite. But okay, if you use a quad, we have a very high spatial resolution, so it's very proximal to the leaves. But if you have a lower spatial resolution, surely I have a lower cost by hectare. For example, images from satellite are free, but I have a very low spatial resolution. Okay, we can divide the sensor, the remote sensor, okay, we can talk about passive sensor that they do not have their own source of radiation, which is why they use the solar one. They measure reflected scatter radiation, for example, near vis, thermal or fluorescent emission, while we have active sensor. They have their own radiation source, for example, radar or LiDAR. Based on technology, we can classify the sensor in optical sensor microwave sensor or panchromatic multispectral or spectral radiometers if they measure one spectral band, 2 to 10 spectral bands, or from 10 to 200 spectral bands. In a hyperspectral camera can measure 224 bands. The proximal sensor Y are non-invasive sensor. They are very close to the object to be measured. We can talk about less than 2 meters of distance from the lips, for example. They allow you to estimate big or fluorescence and many other parameters. Perhaps you have just seen something yesterday. You can collect georeferences data because you are in the ground, you are in the field, so you can take some georeferences data, but perhaps they can be the expensive tools, so they are not so common using in the vineyards or in the States. Satellites. There are different satellite indices of vigor, water stress, and chlorophyll. The most common satellites in agriculture are Landsat 8 and Sentinel-2. There are other projects that can give you, for example, Sentinel-2 or Landsat can give you images. They have the size of the pixel is 10 meter. There are some other provides that can satellite projects that can give you, for example, images with a pixel size of 3 meters, but we have to pay much, I say. And also you can, for example, buy the images from your estate, but you have to buy the images from a large side area. So just for now, okay, perhaps it's preferred for now to use these ones free that to pay something to give to have more precise images. The resolution. We have three different resolution. Time resolution that indicates the period of time between one satellite pass and the next. For example, Sentinel-2 pass every 5 days, but you have a cloudy day, you have to wait for 10 days, for example. Also, we have a spatial resolution in the size of the smallest identifiable surface element in the images, the pixel I just talked before. Spectral resolution is the amplitude of spectral bands distinct from the detector. The multispectral band is larger, is very large compared to the hyperspectral bands because they divide the spectral in 224 bands, while, for example, a multispectral camera can divide it in 5 spectral bands. Okay, when you take the images, for example, of a surface area, you can have historical vegetation index. At the beginning of the cycle, for example, the spectral response is the response of the barrel solid because, for example, you are in the winter time and the NADV values are low. While when as plants merge, the digital values of the crop begin to rise. And then we are going to reach a climax, sorry, when the plants have reached such a development as to close to the plot. The spectral response is only that of vegetation, while in the maturation process leads to decrease in reflectivity in red and then in infrared. Okay. In the case of tree plants, the indices do not follow the crop cycle, but the variation are mainly due to leaf drop or yellowing, catastrophic weather events, insect attacks, or plant diseases. So when you see these kind of graphs and you see some low values, you have to think about what's happened. That's why the agronomic survey in the field is very important because you can read this kind of maps and you can link, for example, low values of vegetation to a special event that has been happened in the state in that year. So that's why always the fields of observation are very important. are fundamental in precision agriculture because they can validate some data that you can take from satellite, from drones, from iPhone, for example. The goal is to synthesize and archive information so as not to lose it, make it available over time and compare with other factors. When you see some field observation, you can, for example, look at abiotic damage, soil type, and anomaly. So it's important to see to have something that can store, archive this kind of informations because you can look and see what happens, where it happens, and when it happens. The first tool that was used at the beginning of the 50 of the last century are the weather stations. Weather station very different from each other. You can have multiply information collected by numerous sensors. It depends by the number of sensors that you have in your weather station. You can have the most common are rain sensor, soil temperature sensor, soil moisture sensor, wind speed and the direction sensor, temperature, humidity, air pressure sensors. This was some images about the most common weather station. There is also a photovoltaic panel, so you have not to be connected to electric gate, for example. And you have a thermometer. You have an anemometer that is very important. For example, if you had to make a spraying, okay, if you have a high wind speed, you have to wait because you can't make a treatments with have a wind speed very high. And also we have a rain gauge. The precipitation is measured in millimeters, and you have to look at what happens every month because, for example, sometimes we have some leaves or insects that can fall inside, and you have to clean because in other way you have not a corrected data, for example. Also, another very important sensor is leaf wetness, because the leaf wetness, for example, for some diseases is very important because we have not to follow only the precipitation, the rainfall, but you to have to see to look at leaf wetness. Okay. Also, installing a special connection interface on the weather station is also possible to install sensor for measuring soil moisture. Okay, are important, but you have to remember that you have the soil moisture value in that place, in the place where you have made place the tensiometric volumetric sensor. So, okay, if you have a field with the same ground, probably you can use for all your field that values and give water, for example, for 3 or 4 hours more if you have some water stress. But if you have different kind of soils, you to pay attention about using that values for all the field, all the ground. Okay. You can also choose not to buy, not to have a weather station because there are some now the virtual weather station. Okay, there is a service, you have to pay it, but okay, you can follow them, for example, for rainfall, for temperature, but for leaf wetness, be careful because the data sometimes are not inaccurate. So, for example, if you have a vineyard, it's preferred to have a leaf wetness sensor because to follow what is going to tell you the virtual weather station. Anyway, you can see, you can find in internet there are some website that propose data from virtual weather stations. Okay. Also, you can for control tools, use thematic maps. The maps we can divide, for example, in soil maps, prescription maps, seeding maps, a yield map. Also, multispectral satellites can give you some NDVI maps, and you can use some of these from specific needs. So we can see, for example, soil maps are okay. Soil is a complex living matrix. You can have soil maps about some parameter that you are going to know. For example, texture, size, pH, carbon stock, and so on. You can have this with some machine, kind of scanner that use electromagnetic induction sensor. They are not invasive. You can to pass on your ground and they measure, for example, the conductivity in the soil. And you know that conductivity is linked, is depends by the texture, the water that you have inside your soil, and for example, if you have high EC values, for example, you have clay, you have compaction, you have a high value of moisture. If you have low EC values, for example, you have a soil that is made mainly by sandstones. Anyway, um, the agronomists have to know, have to see, have to validate these kind of values. Also, you can have some yield maps. They indicate the yield measure in each square meter of the field recorded by the machine. The objective is to correlate operations carried out with the production obtained, helping the choice for the following seasons. For example, to fertilize in a different way. Or for example, you can use to know what is we are going to see after the expected yield for vineyard. There are some machines, there are some cameras that can count the grapes. So you know, for example, your expected yield in July. Why to wait for harvest time to know what is the production after the vintage. Um, anyway, when you want to produce a prescription map, you can use, for example, a drone. You made aerial surveys for with a multispectral camera, and you can produce a vigor or thermal map, for example. You know that with a multispectral camera, you can have different maps like NDVI or NDRE maps. But anyway, as I just say 2 times, the agronomists have to validate this kind of maps, go in the ground to see, okay, there is an area where the vigor is low, so the map is correct. And then, for example, after is going to say, okay, I have to make a fertilization. I have to give 3 different doses of fertilizers. So we can produce with these informations a map of prescriptions. You can load in a machine thermal, and then we are going to make a variable rate machine fertilization, as you can see in these images. Also, we have also some real case studies. For example, these maps are made with thermal camera. Why? Because with thermal camera, you measure the temperature of the leaves. So it's very important because, okay, whenever there is a water stress, the, the temperature of the leaves of your vineyard is going to increase. So, for example, if you want to place an irrigation system in your vineyard, these kind of maps are very important because, as I said before, if you have a moisture sensor, is a very located spatial measuring. So, for example, if you have this kind of maps, you can have a spatial view of where is in your field the areas with more stress. So you can decide, for example, with the prescription maps, the areas when you want to give more water to prevent water stress. We make this kind of analysis, we have to think that, for example, you be careful to not to consider the grass in the interrow areas. So, for example, it's very important when you produce and divine maps and you have to use in in your estate. You have to follow. You have to select only the vigor maps linked to the virus, and then you can after you can produce a prescription maps on the right. For example, there is a prescription maps that is used in the harvest time. This estate use this kind of maps every year to say to tell to the workers, for example, to collect the grapes in the red areas first, and then to go in the green areas because the state of maturation is different. Sometimes the objectives is to make vigor zoning to make different fertilization. Sometimes it's better to make drone surveys with multispectral camera before harvest because with one flight you can give to the farmer the areas that is better to collect before and after. If, for example, the state has variable rate machine, sorry, they can use for the fertilization after harvest. In some cases, possible also to give to the states the place when some fines are missing. So in the past, the Tuscany states, for example, used to sign with some with a sign with a color sign the place where the vines are missing. But this one is better because you can give to the farmer, you can give to the technician a map where every place is georeferenced. So it's very important. And so you can calculate, for example, the number of vines that are missing in your field and you have to buy to replant again. Also, with drone surveys is very important to build some 3D models. I know that you just seen something yesterday. It's very important, for example, to look to see if there is some use a kind of fertilizers and you can see look if your fertilizer looks works better or not. Measuring making a 3D model, you can calculate the biomass. You can link the biomass with some different fertilizers. For example, you make for example a plot test. You can divide the vineyard into areas. You can measure, for example, the using of one type of fertilizer with another's, simply calculate the biomass in two plots. So one is example. Anyway, in precision viticulture, there are also forecasting tools. There are some tools that can try to predict something that probably is going to happen after. So we can divide in weather forecast predictive models of phenology, but my colleague Luisa is going to talk after. Predictive models of plant diseases, forecasting models of nutritional needs, and irrigation forecasting models. Okay. Forecast models can be used for irrigation, fertilization, to prevent diseases and to see the phenology. Anyway, the forecasting models start from real starting data and predict the occurrence of certain dangerous phenomena for agriculture. Are important because they rationalize the use of plant protection products, water resource, and fertilizers. Anyway, also by the climate change, the need to combat harmful diseases and infestations is going to be more important compared with the past. Because with the climate change are coming new diseases, new insects, so you need more tools to prevent or to study or to collect data if there is some, for example, insect in the fields. And within all these models are a representation of a real object of phenomenon through one or more mathematical formulas. We reproduce the characteristics considered fundamental for the objectives they propose. Mathematical models are a simplification that is as faithful as possible to reality. So, okay, there are some structure, they are the sum of some function, but okay, more complex are these models. Probably you have a more precious response, but sometimes you have more parameters, so you have to pay attention on it. Anyway, these models, okay, the diagram, the structure is to find the problem, to make experimental design, to make data collection, data analysis. Also, you try to make a model builder, a training set, a validation set, and at the end you have a DSS, decision support system that can give you some answers starting from data to prevent something that is going to happen. The aim is to reduce crop management costs, increase the quality of products, safeguarding the animal and plant species present in the agrosystem. So just for now is one of the main business about these software houses that proposes DSS. Their power is to have precision models because the farmers, okay, can buy a software but wants to have a real help from the answer that these models can do to the farmers, to the technicians. Um, Anyway, it's not so easy because you have to get data, you have to make the experimental design, you have to make a training test, validation test. Also, if you decide to sell this kind of model, this DSS, okay, I think a software house have to validate also after because a model needs data. More data you can give to a model, more precise it's going to be. Anyway, you have to consider the spatial reference and the time reference. So when you talk about the spatial reference, you talk about operating unit field, while time reference is historical or present or future. That's why we are talking about forecasting tools. There are some models that talk about the phenology, but it's going not to talk about it. And for example, you can have some models that can tell you when you have to harvest some kind of varieties, for example, Chardonnay, Cabernet Franc, Cabernet Sauvignon. And there are two index. One is Winkler's index that consider the average daily temperatures, or ugly index that is little more complex, but they consider the quantity of the temperature from the starting season to the harvest, and can give you, okay, this is time for harvest Cabernet or Gamay or Pinot. With the climate changes, okay, there are some French chateaux that decide to plant some vineyards in UK because they saw that, for example, the temperature were too high for collecting Chardonnay. So now with climate change in United Kingdom, okay, is the right place to cultivate Chardonnay. That's for the this kind of index. So you have to think that some states decide to plant 60 hectares of this kind of varieties that have a low values of this kind of Winkler or Hagley indices. So also you can add some DSS that can give you you show some graphs about these ripening partners. And okay, it depends by the varieties that you have in your vineyard. Also, talking about forecasting tools, we can see the irrigation models. The irrigation model is a forecasting model that tells to the farmer the optimal amount of water to be supplied to bring the soil into optimal condition. The irrigation part is a water balance of the soil layer explored by the roots. It is determined by considering the contributions of rainfall and irrigation, net of losses due to the evapotranspiration. The water available for the crops falls within the range between the field capacity and the wilting point. Okay, however, the efficiency of water used in the soil also depends on the phenological phase of the plant, especially on root development. And anyway, there is the agronomic manage of the field. This is very important. They can impact about the managing of your water resources, for example. Anyway, there are some DSS that sometimes are simply the report the data of the moisture sensors values, and can give you can send you an alert, for example, in your smartphone that you have to irrigate in that period because you have a low values of moisture in, for example, in July. And so you can find in some DSS software these kind of graphs. Also, you can have some fertilization models. The fertilization model calculates the nutrient balance, the inputs, and the losses. So you have in this kind of software, you can put the kind of soil texture that you have in your field, the average monthly temperature, the harvest date, the culture, for example, the data from soil analysis that we just made some years before. And in this kind of fertilization model, you can have the quantity of fertilization, the type of fertilization you have to give to maintain the yield you want to have in the year. Divide for the kind of nutrient that you want to follow to manage. The fertilization model can be combined with vigor indices calculated from satellite images such as NDVI just before for the creation of the prescription variable rate fertilization maps. The prescription maps allow you to optimize the fertilizer dose, associating the most suitable amount for each area of the field. Okay, we know that the variable rate fertilization machines are not so common. Also in Italy are not so common. But for example, I saw that some wineries decide to use this simply saying to the tractorist to decrease, for example, the speed of tractor in the areas where you have to give more fertilizer. So, okay, the variable rate machine is the optimal tool for uses this kind of prescription maps. But I saw in some wineries that they simply change the speed of the tractor, trying to give more fertilizer in some areas than in others. Also very important are the defense models that can manage the probability that you can have the kind of disease in your field. So they are very important and they allow you to optimize the use and quantity of treatment without using calendar fighting that, for example, are not allowed in Italy. You can have we are talking about vines, but you have some models about the disease for olive trees, maize, tobacco, tomatoes, winter cereals. So really, just for now, there are a lot of models. This one, for example, you can see the graphs that are made by a model, a disease model for grapevine down mildew. And you can see that in this graph, what is the time you can need to make a treatment. Generally, they follow the average daily temperature and the cumulative rainfalls. But I have said before, is very important to follow the leaf wetness because, for example, 2 years ago, a lot of farmers here in Italy follows the rainfalls, but they didn't follow the leaf wetness. They have real damages from this kind of disease. Okay, also they are very important, the models that can give you the increasing of population of some insects. The insect grow through phases called stages. For example, you can have an egg that becomes a larva, that becomes a pupa, and finally becomes an adult. We have to follow these stages because sometimes you have to use some pesticide that can be used only on larva, only on eggs, only on adult. So you have something that can tell you which is the right model to make treatment. Also because okay, the pesticide that fight the insects, are very has a high impact about environment. So you have to be very careful using this. Also, there is some forecasting tools about the frost risk. Generally, they use the following inputs like minimum temperature, average temperature, dew point, and maximum wind speed. In the last years, there were some vintages that have the great problem about this kind of risk. We can we can categorize the risk of frost in the normal frost, that is what layer of ice crystals form on the ground you can see in the morning when you go around the vineyards. Also, it's very dangerous if you have the young grape shoots. Also, the black frost, that is distinct event from frost because fewer non-ice crystals form on plant surface, but because the temperatures are very low. But okay, you can do anything on it. And also sometimes you have also mix of freeze. It depends, but the values of temperature that you can have in the night. In some days in April, for example, also in May sometimes. And also you can have some DSS that can give you some alert or some graph about the risk of frost in your field. Okay. And then we go on talk about decision making and prescription tools. You can data and comparison dashboard, overlay mapping, and prescription maps. Um, as I just said before, the DSS is the most common tool that has been adopted by the states because thanks to the summary of a lot of data of the situation by your crop field or production sample, it is possible to establish targeted intervention and actions. The overlay mapping is very important because is a computerized information system that allows the acquisition, recording, analysis, visualization, and return of information deriving from geographical data. And also, the map is the way you can manage a virtual variable rate machine, for example. The prescription maps are this kind of tool. You can produce from satellite, from drone, from quad service. You have to need the field information. Also, the technical knowledge is very important. For example, to indicate the amount of fertilizer, treatment, seedings to be administered in each area of the field. And then with prescription maps, you can make fertilization, treatment, or seedings, or for example, also the harvest. After we are going to see some machine that can do this. The construction of a prescription maps involves three phases. Identification of homogeneous area of the field in which the same dose of nitrogen should be administered. Identification of the fertilization strategy. Identification of the correct dose of nitrogen to be administered in each area of the field. Generally, the prescription maps are in a shapefile format and can give you the dose of active ingredient, kilos by hectare, or hectoliter liters of fertilizer, pesticide, or seeding dose, for example. Okay. Just for now, we can talk about the implementation tools. The implementation tools regarding of automatic guidance, parallel guide, variable rate technology, and actuators. The automatic and parallel guidance, the advantages is increased working comfort and simplicity. Reduced product usage, reduces plant stress losses, increase the work efficiencies with reduced visibility. For example, you can use automatic guidance in the night. For example, sometimes you have to harvest in the night. The automatic guidance would be a great solution for this. Also, you have a reduction of diesel consumption and to make the possibility of strip tillage, for example. It's very important the system which you want to adopt to use the automatic guidance. You have the GNSS, that is Global Navigation Satellite System. Um, they are systems occupied with receivers that, by intercepting the signals emitted by satellites, are able to determine their position on Earth, but they are not so precise. You need the RTK. Real-time kinematics applies a correction to satellite data distorted by tropospheric delays, offering centimeter precision. So if you want to make a fertilization, if you want to harvest, it's better to produce a prescription map with real-time kinematic. It's better. Okay. Anyway, managing variability means that the production process, once the information has been gathered, is applied in a diversified way. The methodologies for dealing with variable distribution are with maps or with sensors. With maps, I've just talked about it. With sensor, for example, there are some sensors like LiDAR, ultrasonics, multispectral cameras that are mounted on side machine. For example, you can see in these images, this is for treatments, and you have some LiDAR sensor. Okay, probably, okay, you can manage, you have a very precisions using, for example, pesticides or fertilizer. But anyway, there are some sensor, they are mounted on tractors, so they can break. They are expensive, so you have to, when you buy, for example, a new sprayer machine, you have to think about it. You pay, but after you have to manage that. Okay, are delicate sensors, so you have to think about it. Anyway, it's very important when you are going to use variable rate technology that everything can talk. Okay, the computer can talk to the tractor, it can talk with variable rate machines. Is not very common because okay, the language is a bus, but I can assure that. Okay, sometimes there are problem about the communication from computer to tractor, computer to machine to sprayers. So we have to work a lot on it because we have problems. Now we have problems on about this argument, the isobus, because every company that produce machine try to make some little difference, but anyway, it's a problem because you have to use the same languages for all the machines because the farmer, the state has not a long time. Also in this period, they can't have a problem about the communication between the tractor and the sprayers. They have to make the treatment tomorrow. They can't follow these problems. So one of the aims is to try to have machine that talk the same language. I can show you some machine, this variable rate fertilizer spreader. This is variable rate sprayer. Okay, this has some sensor that can recognize the disease in real time. But as you can see, this kind of machine is a little bit complicated. So I think that okay is useful for research, but in the States you have to we need simple machines. We can't think to use this kind of machine with a lot of sensors because a lot of sensor uh, carry also the needings of to be careful to manage to calibrate the sensors and so on. This is a variable rate defoliator. They can read, for example, any DVI maps. Can defoliate the part of the vineyards that you have too many leaves, and this is the variable rate grape harvester. Okay, as you can see in the photo on the right, there you can see a map with only two classes. That's why this kind of machine can separate in only two classes of vines, of grapes. So we have grapes with uh, that comes from part of the vines with high vigor or low vigor. And then also when you are going to bring these grapes in the cellar, you have to prepare two different lines because you want to send two different tanks the grapes that comes from high vigor zone and low vigor zones. So it's important because in a different way this machine is not useful for you. Also, in the future, we are starting to see some robots. On the right, you can see a robot that can make the pruning. I think, okay, we are going to wait a long time to see this kind of machine using in the vineyard. And what about spraying drones? There are a lot of estate that really wanted to use spraying drones for make treatments in vineyards. But okay, I think that is a very effective tool for low water volumes. The product distribution depend on too many variables like speed, height, nozzles. Also, in Europe, there is not homogeneous regulation. For example, in Italy, you can make spraying on a vineyard only if you have a special authorization, and you have to send this kind of authorization for an experimental plot to the minister, and the minister takes 2 months to give the authorization to doing this. So, okay, there are some states that use these spraying drones for make fertilization, but I'm sure that sometimes they put some pesticide, they do the same, but okay. It's not legal just for now in Italy, while for example in Switzerland or in France you can use it. Also, there are some robots. There is a project from France. This is a BTBot robot that can be. We can see some of these in some wineries, also in Italy. But the problem is that these kind of robots are managed by the farmers, but the control of this kind of machine is only with mobile connection, and if you have some problems is managed only by the from the company in France. So all the machine are collected with the company site. So you have to call the company and say, "Oh, I have a problems," and remember that just for now the connection is only with mobile connection. So, if, for example, you have a vineyard, you have no signal, there is a problem to use a VTBot. On the right, you see a robot that is used for collecting data. Sorry. Okay, to collect all this data, you need a web app DSS. There are some software houses, I saw that also in Montenegro, there are some that collect all this kind of data. So the farmer, the technician, tech manage, and sometimes this kind of is our web app DSS. There are also, sorry, what happens? Sorry, I have a little problem.
It is okay. We can see now. It is what is.
No, 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 but it's a problem. Sorry,
Okay.
I'm going to share it again because sometimes the PowerPoint presentation have some problems.
Mhm.
Okay. Mm, let's start again. You see now?
Uh, we will be, I will be soon, just a second. Yes, we can see it.
You
You
see
can put it in
now?
the presentation mode if you want. Yes.
Okay, perfect. We can go on. Okay. There are also some mobile apps. There is, for example, a mobile app that can make the scannering of the vines and then can produce a digital twin. The digital twin is used for giving to the farmers the vigor of leaf surface, the optimal dose of water and pesticides. And if you repeat the scans in minimum 5 points, you can have of a map of vegetative variability, and you can use this app for reducing cost, improve yield and quality, reducing bugs, because you are going to give the dose of water and pesticide not linked to the ground but linked to the digital twin, to the surface, and you have some water saving, for example, or pesticide savings. Also, there are some cameras that can count the grapes. There are some special cameras that are mounted on tractors and can count the number of grapes. It's very important because you can have, for example, the expected yield of your vine in June, in July, simply counting the grapes. So it's you could be, for example, a useful tool for a cooperative that wants to know by the partners what is expected production they are going to bring in the cooperative cellar, for example. And they use the process of image learning. So they start to counting the grapes of the berries. Okay, there are some companies that propose, for example, they can monitoring the grape ripening, the disease detection, but we have to be careful talking about the disease detection with the image learning. Okay, this is from some of the maps or the graphs that this kind of solution can give to the farmer. As I said before, there are some mobile apps that can recognize the vineyard disease through image learning process. I just show you a company that proposed this. Okay, I made some, I try to use it and probably can give you the right answer for the common diseases. But if you try to ask to the ER to know the right disease. Okay, we are not in the right moment to use this. We have to wait a little bit because um, there are the first application of artificial intelligence, so we have to wait a little bit. But perhaps in the future we could have robot workers, for example. We don't know. So okay, these are the perspective and the what is probably you can see in the future in our vineyards. But for some application, we need time because just for now we start using some of the tools of the I've just shown you, but for example, like Isobus, there are some problems because we have to make a kind of modernization of the language for all the instruments of the tools. So I've just finished. Thank you for your attention. If you have some answers about what I've just showed to you, I'm here.
Thank you, Nicolo, for your presentation. I would like to ask the public here present, do you have any question? Yes, but wait for the microphone.
First of all, thank you for your presentation. I have a question about the price. How affordable are these tools you've been showing us for a common man, for someone who works this as a maybe side job or a hobby? Or to be more precise, I want to ask which one is the cheapest or easiest to get or easiest to use? Thank you.
I can give you all the prices of the tools I've just shown you. For example, for drones, for monitoring drones, the cost is between 3,000 euro to 5,000 euro. If you want to buy drones for spraying, you have to spend 20,000 euros. For weather stations, the common price is 2,000 euros, for example, while for the DSS, there are a lot of software houses, but you have an hour rent that comes from a few hundred euros to thousands. It depends, but generally they calculated the annual rate by hectares. Also for the machine, okay, you can spend from 15 to 20,000 euro for a fertilizer rate machine and feel, for example, the grap ripening machine. Okay, you are talking about 100,000 euros. So you have to be also VTBot is going to cost like an apartment in Florence, like two or 3,000, 200,000 euros. So only the great wineries can afford this kind of cost.
Thank you, Nicolo. Do you have any further question?
Nicola, thank you for a great presentation, great overview of technology. I have one question that is related to RTK modules and the autonomous of tractors. So you said that the main problem is intercompatibility between different producers. So are there some open source initiatives that can handle this issue to standardize a way of communication different equipment? You know, the main problem for agriculture producer is he can start with one equipment. So if he start with one equipment, it is really hard to make an upgrade by selecting different producers. Yeah, and in some cases, a lot of agriculture producers in Montenegro are having public tenders in order to procure their equipment, and it is really hard to in this kind of public tenders you cannot specify I want equipment from this manufacturer. This is really hard to accomplish here. This kind of interoperability between these kind of equipment. So what are your experience with this?
Open source would be a very great solution, but yeah, just for now, every company propose his own solution, and they say my one is the best, but you have to pay. So this is the first problem. The other problem is, for example, the automatic guidance. Mm, I prefer if would be a farmer to buy someone to can assure the automatic guidance, because okay, if for example if one error happens, okay, the tractor can go on a row of the vines, so it would be a real problem. Anyway, there are some companies that try to sell a kind of kit that can be applied on the common machine, and the farmer can spend less. For example, one of these is an Italian company. I have no relation with them, but they are Arvatec company. They are placed in the north of Italy. Some years ago, used to sell some kit for automatic guidance to transform, for example, fertilizer, invaluable rate fertilizers. Anyway, they transform machine that has just now a computer, because without computer is very difficult.
Thank you.
Yes, thanks again, Nicolo, for your presentation. And I suppose that we can move forward to our next presentation, which will be held by Luisa Leolini, and in the context of crop modeling, general concepts and application in the multi-layer vineyard systems. Thank you, Nicolo, again. And Luisa, please try to share your screen. Thank you.
Okay, hello. Can you hear me?
Yes, perfectly. Thank you.
Okay, just one moment. I'll try to share the screen. Okay. Can you see the presentation?
Yes, thank you.
Okay, try to minimize this. Okay, so hello everyone. I'm Luisa Leolini, and I'm a fixed-term researcher at the University of Florence. I work in the research group of Professor Marco Bindi, and I work on crop modeling since my PhD. So my PhD started at the end of 2014 and ended at 2018. And I work during my PhD thesis on an implementation of a vine model for simulating vine development and growth under different pedoclimatic conditions. After that, I work always at the University of Florence with some postdoc contracts, and always working on crop modeling and the impact of climate change on crops with different crops, not only vine, but also olive trees and other annual crops. And with my recent contract, I'm also trying to model the biogeochemical cycle in the agroecosystem. So the main cycle of carbon and water, especially in agropastoral system and in vineyard. So today I thought to present this work. Is titled Crop Modeling General Concepts and Application in the Multi-Layer Vineyard System, because I was thinking in the room probably there were different type of knowledge about crop modeling. More of some of you can be, for example, beginners in the use or in the development of crop models. Some other are more familiar with them. So I decided to start from general concepts to go through model applications. I want to also say thank you to invite me as speaker in this very nice event you organized. Unfortunately, as you notice, I'm not there, but I hope I'll be able to come in the next future. So my presentation is organized like that. We have different points. The first two are more general concepts about crop modeling, what is a model, and which type of physiological process can be simulated with crop models. Then the point 3 is more related to model application. Model application that are generally model are used to simulate in present and future scenarios to evaluate the impact of climate change in present and future climates. But also with the new technology, the new sensor, models can be coupled also or integrated with data from precision agriculture. So I'll show you an application we performed in our group about grapevine. So how to use data derived from a sensor to force a grapevine model to improve the spatialization of the output. Then some model strengths and weakness, especially related to this type of models, respect to empirical regressions. And then point 5 and 6 are two case studies. Point 5 is related to what we are doing now. So it's a preliminary study about Montenegro. And for this reason, I want also to say thank you to Sania and to all of you for the data you provide me. And point 6 is another case study, is in northern Italy, is a vineyard in northern Italy, in which we are simulating not only vine, but also the interrow in the vineyard. So we are moving from an original solution which simulate vine, exclusively vine, to a vineyard model, so which include not only the main crop, but also the grass in the interrow. Then point 7 is more related to fluxes, and actually is what I'm doing now. So I'm trying to remodulate our model solution to account for carbon cycle. And I hope in future I'll be able to do that also with nitrogen, but currently the fluxes we are able to simulate are carbon and water. So I did that, and we published in our group this paper this year about a model to simulate grassland, and I'll show you this model because we are trying to do something similar to vineyard, to the vineyard. Then we summarize the conclusions, and I have also some suggestions for you about some books you can read about modeling and precision agriculture. And then a communication, my last propaganda and communication for you. So let's start with general concept. Okay, when we talk about a model, we talk about many things. And I saw before the presentation of Niccolò also, he used this word for many different solutions. When we talk about crop modeling, generally we talk about crop models. And for crop models, we mean process-based model. So model that simulate different processes. Actually, the model is a simplified representation of a system. So a simplified version of the real world. So what is a system? A system can be everything, but being the name crop models, you can guess that a system can be also a crop that has a delimited part of the reality, of course, because it could be very difficult to simulate everything. So we have to focus on crop, also because behind the development of a model, there is, of course, an objective. And our objective can be, for example, to estimate crop production. So we focus on the process that allow us to estimate crop production. This delimited part of the reality, so the crops, is composed by different elements. So it's composed by organs. For example, a crop can be composed by root, by so the below ground biomass, the above ground biomass, so the leaves, shoot, fruit, and you know everything. So it contains interrelated element and process that are simulated with crop models. The crop also is situated in an environment and interact with different parts of this environment. it interacts with the atmosphere, so with the climate, interact with the soil, so the water, for example, or the nutrient in the soil, interact with human beings, because we are talking about agroecosystem, so the effect of human practices in the agroecosystem is very strong, and the growth of crop in a natural environment is not the same of the growth of the crop in an agroecosystem. So it should be taken into account using crop modeling. For example, in vineyard, you know very well that vine is pruned sometimes. So in the model, we have to be able to simulate this reduction in biomass when the event, the agro-management operation occurs. So these processes and all the interrelated element and the system, the entire system we want to simulate is simulate using mathematical equation. And this also, Niccolò point out this aspect, because many type of model can exist, like graphical models, physical models, and so on, but we are talking about mathematical models because we use different algorithms for estimate the different processes. So what is a crop model? A crop model is a quantitative description of these different processes that provide specific outputs. Here I just make an example of two outputs, for example, the biomass of the crop or the yield, but they can have many, depends on the complex of and the structure of your models. These processes are simulated separately, generally. So the processes are simulated with an implementation of the code that simulate that specific process. But then they are aggregated to simulate the entire system. So this is an example, a workflow, the way we use to represent a model, for example, in the paper, but whatever, because it's a user-friendly way to show how the model works. So in these little boxes, we have a description, for example, leaf area index. This means that inside of this virtual box, let's say, we have an implementation of the code that is able to estimate leaf area index. Leaf area index is connected with the next box because light interception is based on plant leaf area. So this is why light interception use the output of the first process to simulate light interception. And so on. After light interception, photosynthesis, dry mass production, and the partitioning among the organs. From leaves, from leaf biomass, it's possible then to calculate again leaf area index. So this is the way, a very simple workflow. This is, if I'm not wrong, is a model about tomato. But this helped me to show you how generally the structure of the most famous crop model that you can find available online and in literature is done. So this is the base to how to build a crop model. Generally, the main crop models simulate directly net photosynthesis. This means that they don't simulate plant respiration, but directly net photosynthesis. And I'll show you later why we are trying to remodulating this part to account for plant respiration and thus to simulate the carbon fluxes. So this is an overview. I don't know if you can see, but this is an overview of the main crop model you can find in this review. It's Jean et al. 2018. At the end of the presentation, I just have some slides with the reference, so you can find everything there. It's a timeline from 1965 to 2020. In which you can find the main crop models that are developed around the world. Here you can find the different countries. Of course, probably there are more, but at least this is what Jean reviewed in his paper. And even if he showed that some models appear in 1970, the most important activity in developing a crop model was from 1980 to the middle of 1995. And now the current version are continuously updated. For example, in US today, the most used model is DSAT. DSAT has many versions, as you can see. In France, STIX, probably you know, it was updated also and implemented to simulate grapevine, because at the beginning it was developed for other crops, but after the PhD thesis of Garcia de Cortazar Tauri, it was also adapted to simulate grapevine. Here, STIX in 2020, the last version, the last release was 8.4, but I had the course this March about STIX, and currently we have version 10. So this means, and this show you how the current crop modeling solution are continuously implemented. At the beginning, the model were the model moved from qualitative representation of the system to a quantitative representation of the system. This means that, okay, I can tell you if the crop grows, but I can also tell you how much is growing. So, for example, my biomass accumulation can be 100 gram dry matter per square meter. So it is possible to quantify the different process, and also change from the simulation of single process to the simulation of many processes. So as you saw before in the workflow, in the very simple workflow I show you, from 1980 and moving toward now, the crop model become much more complicated and start to introduce many more processes. So, talking about physiological processes that can be simulated with crop models, generally most of the main famous solutions start to produce these different production levels. So, for example, at the beginning, after the simulation of phenology, because phenology is important to simulate the main phenophase and to define the phenological and the development cycle, the production of biomass is simulating starting from potential biomass. The potential biomass is based on some weather characteristics like radiation, temperature, and CO2 concentration in the atmosphere, and from crop parameters or crop characteristics. So this potential biomass is the first level of production that is simulated. After that, the biomass is reduced, and is reduced, for example, by the effect of water stress. Because, for example, we know very well, especially in Mediterranean area, that in summer is very dry, so we can have the effect of water stress that affect, for example, the leaf development or the relative transpiration. So this can reduce, again, our biomass. From potential, it becomes limited by water. And it can be limited also by nutrients, by the effect of, for example, nitrogen stress, or other cycles, other elements like phosphorus, even if this type of cycle are not easy to simulate, and the main cycle that is simulated currently in the most famous models is nitrogen. So the nitrogen effect, the nitrogen stress can reduce again the biomass until other effect that can be implemented in the model can reduce again our biomass until we arrive to actual biomass. And this effect can be the effect of weeds, the effect of pest, the effect of disease, pollution, whatever you are able to simulate and to convert little by little our potential biomass into actual biomass. This is more or less the structure of the production level you can find in many solutions, many modeling solutions. So, like, as I told you, like physiological processes, generally, one of the first process we simulate in the crop models is phenology, because as I told you, phenology defines the development cycle. So it's possible to simulate the bud break when it occurs, the flowering time, for example, the veraison and maturity, if I am talking about a vine, for example. And this is important because, for example, you know very well that in the crop development, at some point, the vegetative biomass, the biomass that is produced by the crop change from vegetative to reproductive. And this change is defined by flowering. So when flowering occurs, fruit set occur, the crops start to partition part of the biomass into the fruit. So if I'm not able to define well flowering time, I can have problem to simulate yield, fruit biomass, and then yield. So then, as you saw before, after phenology, or for example, after bud break, the crop start to produce leaf. Leaf is calculated to define the plant area. Plant area is used to estimate the light interception. And this is a graph about the two types of chlorophyll, A and B, and the wavelength in which they absorb the sunlight. So after light interception, we are able to estimate photosynthesis that, as I told you, generally is net photosynthesis. So we use radiation use efficiency to convert intercepted part into into biomass. So we obtain the potential biomass, and then we reduce this potential biomass with stresses. For example, this is the first graph here. Is not about the grapevine, it's about the olive tree, but more or less the concept is the same. Here on the e-axis, we have FTSW, which means fractional transpirable soil water, is an index from 0 to 1, is 1 when we don't have stress, is 0 when we have stress, water stress, of course, and is typical to have water stress in summer in our region. So generally it decreases after spring until value close to 0. And this fractional transpirable soil water is used to evaluate, to assess the impact of water stress on grapevine, on crop in general. Generally, this FTSW is derived by data of soil water content, of soil water content in this case, but if we have nitrogen stress, for example, soil nitrogen concentration, and with this index is possible to convert finally our potential biomass into actual biomass. Then the biomass is partitioned among the organs. Here is an example we are trying to implement in our vine solution with the partitioning among different organs, shoot biomass, fruit biomass, leaf biomass, but we have also the trunk, we have also the root. So at the beginning, as I will show you in the next slide, the model just partition biomass in vegetative and reproductive. Now, in vegetative biomass, we have leaf and shoot, And we have, for example, fruit for reproductive biomass. So we are trying to partition in biomass in different organs. And this is according with the occurrence of the phenological phases. So this is how the model works generally. Of course, depend of the structure of the model, depend of the complexity of the model, but basically these are the main way in which the physiological processes are simulated. So here I propose you some model application. This is an application, is not an application of a crop models directly, but is a phenological model. So this means that is able to simulate just phenology, and indeed the name of the model is Unishield. This model was developed by Shuin in 2000 for arboreal tree, but then was adapted also to simulate grapevine phenology. And here, this is our study from 2018, in which we try to simulate with this model bud break and flowering date of 4 different grapevine varieties, which were Merlot, Cabernet Sauvignon, Chardonnay, and Glera across Europe. So we use a performance calibration from our colleague from University of Padova, and we apply the model under different climate scenarios. You can see here on the column RCP 4.5 and 8.5 in 2 different time slices at the middle of the century and at the end of the century. And we use, in this case, just one climate model at 50 kilometer spatial resolution in Europe. So what we can see is that both phase, flowering and bud break, occur earlier in future, especially in the middle of Europe. So there is an advancement of both phase. This advancement is more pronounced for bud break than for flowering, because flowering is a sequential phase that is also affected by the movement, by the shift of bud break. So it occurs in a time that is not so, in which the forcing units are not well accounted because it's too cold, okay? So this means that then flowering phase can occur, can reflect less the effect of climate change in this case. So in Southern Europe, especially in Mediterranean area, in western part of Europe, we notice that we have sometimes the model fail into simulate bud break, because this model was based on a mathematical approach with taking into account the effect of chilling unit and the effect of forcing unit. So the chilling unit are calculated on specific range of temperature, and if the temperature is out of this range, the chilling unit are not calculated. This is why in Mediterranean area, probably because it's too warm in future, the model fail into the simulation of bud break. Then we have close to the effect of climate change on the main phase, bud break and flowering, we have the effect of frost events. The frost events were calculated as minimum temperature below 0 degrees in 7 days around bud break. And also we can see that there is an increase of frost events in the middle of Europe because bud break is shift earlier, while we have a decrease in the western part and Mediterranean part of Europe, because temperatures are completely different, and also bud break is less shift. Then we have fruit scent index, another index we calculate, and fruit scent index is calculated as a suboptimal temperature around flowering. So we take into account that flowering, the optimal flowering occur at 25, 26 degrees. So temperatures that are below or above this limit reduce flowering. So, and this has an effect on fruit yield. So in this case, the range is quite wide. This is why the difference you can see very well is not well defined, because the range we calculate and the empirical relationship we obtain take into account a large range of temperatures. So, but in general, in Northern Europe, this fruit set index improve in the future compared to the present. So, talking again about model application in climate scenarios, probably my colleague from Utah know very well this, this study, because this is the study of Fraga in 2016. And this is an application of a crop model, a sticks model, in Europe. Here I just use two variables, leaf area index and yield, to represent the application of sticks in Europe. On the left panel, you have the absolute value, so the absolute value of leaf area index and yield in tons per hectare. And on the right panel, you have the difference between the present and the future, so for both variables. Okay, the climate scenarios Fraga used in this study is RCP 8.5. And being difficult to adapt the model to different grapevine variety across Europe, Fraga used Pinot Noir variety, which is one of the most cultivated grapevine variety and used for wine production. So he adapted this variety and simulated this variety across Europe. And you can see again that in Mediterranean region, leaf area index decrease compared with the present, in future compared with the present, while, and in the same way also yield. So especially you can see here in southern Spain, where the climate will be extreme probably in future, we can have a big reduction of grapevine yield. So this is a way to use, the main way to use model. Indeed, Nicolò before called the model forecast model, not to, because the model are used to predict, to simulate something, to forecast. But with the new technology today, grapevine and crop models in general can be used to apply precision agricultural strategies. So they can be integrated with data derived from sensor, remote sensor, proximal sensor, to improve the simulation and the spatialization of the main output. So these are three ways in which the model can use this data. You can see here the point, there is the legend below. The point are the remote sensing observation. So each time the remote sensing observation is collected, in the first panel, the remotely sensed state variable, and in general, the model can be recalibrated. So in this first approach, the parameters of the model are recalibrated using the information, the observation from sensors. Each time this information is collected. Then we have the forcing. The forcing is the second approach in which the data derived by sensors are used to replace the simulation. Each time the data, the observation from remote sensors are collected. And finally, the last approach is the approach C, updating, and basically is not the same of calibration, but is similar. In this case, the model state variable is updated with the observation derived from remote sensing. The parameters are not changed, but the model state variable is updated each time the observation is taken. So in our group, we perform this type. We performed this study in 2021. I don't remember when we start, but basically we try to improve the output resolution of our vine model, because the resolution of a model depends on the resolution of the output. This means of the input, sorry. So this means that if we have this vineyard, and here we have one weather station, and here we have one type of soil, the output, for example, grapevine yield, has the same resolution of the input. So we have just an average yield for the entire vineyard. So this means that if we were able to have more weather input, more soil input, and so on, we potentially are able to spatialize our results. So what we have done, we got information from Sentinel-2 that you know very well, and Niccolò explained before me, so I'll not stay here to explain about Sentinel-2, but we got the image from Sentinel-2, and we got one image around fruit set in this vineyard that is located in Tuscany. And we derive the vegetation index we need. In this case, we derive NDVI, that you probably know very well. But NDVI is not a variable of our model. So we need to convert this NDVI in a variable that we can introduce, we can have in our model. For example, the fraction of photosynthetically active radiation, so the FAPR, the intercepted radiation. But also it could be leaf area index. So some relationship between NDVI, FAPR, and leaf area index exists. So we were able to derive our model state variable. But we have a big problem. Also, Niccolò showed before, because you know that in a pixel of Sentinel, that is 10 meters resolution, we can have the vine, but also we can have the interrow, and we want the information of the vine. So if we use drone, it's quite easy, because drone has a very high resolution, so at centimeter level. So it's possible to extract NDVI from the vine canopy. But in this case, was not possible. So we need to rescale our variable in the pixel, and we use the canopy cover from a drone flight. Okay, in the same time, okay, at fruit set. So from the canopy cover, and we use a linear regression to rescale the FAPR, and we were able to extract directly the FAPR of the vine. So we use this information to force our model, so to replace the simulation at fruit set of FAPR, and to spatialize the results. So at this point, we don't have an average yield for the entire vineyard, but we have a yield, a fruit yield, for each pixel of Sentinel that we analyze. In this case, we have two different areas. This is the observation on the left. This is the simulation on the right. We have different area. At the top of the vineyard, we have a high productive area. In the middle, we have a low production area. So in this way, we are able to discriminate the yield inside of the field. So to estimate the subfield variability of the, in this case, of yield. And we are able to do that using an image at fruit set. So, because potentially you can tell me, okay, but why you don't use an image close to to the yield. Probably the simulation would increase. But in this case, we want to provide a very early information to farmer to be able to manage and to optimize the management in his field. So this was an application for precision agriculture. And this is the main application I'll show you today, using this type of model that I told you at the beginning. These are called process-based model. And I think this definition is quite good because it's easy to understand that these models simulate different processes, and these different processes are then aggregated to simulate the crop. This model has some advantages, of course, and some disadvantages. One of the main advantages is in the code it's possible to implement nonlinear regression. And this is quite important, especially in biology, because most of the relationship and most of the process are not described linearly. So this is potentially one advantage. Then they provide detailed information, and the detailed information depend on the level of the structure of your model. So you can have very complex model that simulate many processes, and this and also they simulate with high level of accuracy. But then you can have other problems. So provide detailed information is good, but also it deal with other things that we will see later. Then this type of model are continuously implemented. You saw before in the timeline, in the overview of the main crop model that are used worldwide. Because when you start to develop a model, you learned before from the observation you have in the field from the data, but you continue to learn when you develop the model. And so this is how the research go ahead. So this type of model can be implemented in many ways. And one approach we use, at least in the group, is that we don't replace, in general, we don't replace the original solution, but we provide an alternative to the original solution in which the user can decide which type of process you want to simulate. For example, for phenology, we can have the approach based on chilling forcing unit. We can have the approach based on growing degree days units, so thermal unit in general. So the user can activate one approach instead of another. So it's an alternative to the original solution. Then this type of model has generally good robustness. This means that differently, especially differently with empirical model, they can be calibrated in a specific site with specific experimental data, but then they can be validated in another site or applied in another site. And generally, the performances of the model, if well calibrated, is quite good, is maintained also in the validation procedure. This is not the same generally with empirical models. Empirical models that generally work very well in the site in which they are calibrated, but when it's the moment to validate, they can give very different responses. So as disadvantage, of course, more the model is complex, or more the model is simulates different process, more you have large computational efforts. So today, with the facilities we have, probably this is not a very big problem, but it was in the past, and sometimes it's still in the present, because if we have to perform many simulations, we need this large computational effort, so it could be a problem to simulate. Then this type of model need to an adequate training to be used. Some of these, like crop cyst, I'm not sure you are familiar with this type of models, but crop cyst has a user-friendly interface. Even though at the beginning, we need to train the user, because it's the first time maybe they see something similar, so it's the first time they use this tool, and it's not so intuitive to be used directly, or at least in general, not like that. And the result should be interpreted. So in our case, for example, we have our model that are just code in R. So if you don't know R, it's difficult at least to run the model. But at the same time, it's also difficult to interpret the results that the model gives. So this could be a disadvantage. Then also this last disadvantage depend on the structure, on the complexity of the model, because sometimes they require many inputs, or require specific inputs. For example, our solutions are generally simplified solution, okay? And most of them, I think all of them, do not simulate, the nitrogen cycle. But if I simulate nitrogen cycle, I need this information for initializing my model. So if I don't have this information, it's not possible for me to run the nitrogen balance. So you obtain a more complex model, a more accurate model, but you have to be sure that you are able to run the model, otherwise it's an unuseful tool. So these are more or less the general overview of the crop models. Okay, let's start with the first case study. This is what we are doing now, is a case study about Montenegro. And I want to say thank you again to all of you for the data and for the picture. Probably you know more, very well and more than me, the condition in Montenegro. What I learned is that it's quite warm in summer and quite dry, so you need sometimes to irrigate the vineyard, something that is not allowed here, at least not always. But you have also very big difference in precipitation from the coast to the mountain, of course. And I learned a little bit about Plantage, a very big vineyard, from which I got the data. The data were about these two varieties. I simulate these two varieties. There were much more data, but I start with these two. The first one is Vranat, and for me it was the first time I calibrate this variety because it's not common here. The other is Cabernet Sauvignon, is very international French variety. So in this case, I was able to simulate. First of all, I got observed data of phenology from different sites and wineries, because for calibrating the model, we need a sufficient number of data to calibrate. So in this case, it was not possible to have this number of data because I have just 1 or 2 years. So for this reason, I use different locations. And I got observed data for bud break, flowering, variation, and maturity. For Cabernet Sauvignon, I will not plot, I didn't plot the results of phenology because we do not have enough data for bud break and flower. Then we have a lot of data for yield in plantage, and these were the trend of grapevine fresh yield that then I convert in dry matter because the model simulate in dry matter, so I use a static coefficient to convert the yield from fresh to dry yield. In this case, we have Cabernet Sauvignon that in 2018 has a very, very low yield, but we are investigating also the why this yield is very low in this year. So in this way, what I did is to use the model. The original version is the workflow on the left. In this case, the model was a grapevine model, so it simulates just grapevine. You can see here because in this workflow was not possible to introduce, but also, of course, it simulates a water balance. In this case, the model was built and was developed in a software environment that is called Bioma, Biophysical Model Application, in which it was possible to share input, output, and different approaches. This is why the water balance is not our water balance, but was developed by the University of Milan. And this is why you can see here, but we obtain from that water balance the variable we need to estimate the water stress. Now, what we are doing is to convert this model into a vineyard model. So take into account the main crop, so the grape, but also the grass. That, of course, is an important component of the vineyard. Also, we have our water balance. And we are trying, and we will see later, to estimate the carbon turnover into the soil using a very famous solution that is available in another version, let's say. We adapt to our solution, but it's freely available online. So we set the simulation. For setting the simulation, we need some weather input. The weather input we need are daily maximum and minimum air temperature in Celsius degree, daily precipitation in millimeters, and daily global solar radiation in megajoule per square meter. And we got this information from this weather station that I learned is the closest to plantage vineyard. So these are the basic weather input we need, but potentially we can introduce other weather input. For example, if you in your solution are able to estimate the reference evapotranspiration with Penman-Monteith method, you probably need the wind speed. So wind speed become a weather input that you have to add as column to your weather input file. We don't have, so we use these three basic weather input. Then we have the soil. The soil information we need are the maximum soil and root depth, because in this layer we are able to estimate the soil water content. So it's important to define the maximum depth of the soil. And then we need the available water capacity, which is the available water that you can find between fill capacity and wilting point. So the available water for root uptake. If we have this information, we can define our soil water dynamics. In this case, if we don't have directly the available water capacity, we can derive these hydrological properties property from soil texture, for example, from the percentage of clay, silt, sand, and if possible, also organic matter, and with using a pedotransfer function. So in this case, probably this is not a variable that is directly available sometimes, but is sometimes you find soil texture, for example, so we are able to estimate this variable. If you want to simulate soil organic carbon trend in the soil, of course, you need to initialize your soil organic carbon content. So you need to have this information. In this case, I don't introduce here because I was not using. So then you need to have some information about management. You need to have, for example, the information about the pruning, how many times you go in the field, and we assign generally a specific level of pruning. If it's not too intensive, we apply a specific value to have a not intense pruning. But if you have this information, of course, it can be helpful for us. Then grass management, irrigation, and basically these are the management we are able to simulate. So I told you this was a preliminary study. Unfortunately, we don't have a very good simulation for phenology yet. We have good simulation for bud break and veraison, but not for flowering and maturity yet. And this could be because our solution are not able to estimate some extreme event, especially in summer, or because we need to validate more on other data. So these are very, very preliminary results, but at least for now, we are not happy with phenology. We are more happy with the yield for both variety. And this is more or less the trend. You can see the statistics below, but I don't want to bore you about this. But we are able to simulate, despite we are not able to simulate very well phenology, still fruit biomass is still good, and is for my experience is not bad results for the simulation of grapevine yield. So this is about Montenegro, what we are doing. Also, we are trying to simulate sugar content, because in the vine solution, we have also some specific process that calculate Brix degree, that simulate Brix degree, and titratable acidity. So basically, these approaches are quite similar to the approach simulated with sticks, based on thermal time and canopy temperature. And we are trying to do that also with the data from Montenegro. So this is another case study. This case study is performed, and the study is performed in northern Italy, in this vineyard. This vineyard is called Tenuta Cannona Experimental Vine and Wine Center of Agrion Foundation. And I want to say thank you to the colleague from CNR Stems, and in particular to Marcella Bidocco for the data, and to the colleague from Agrion Foundation. And in this vineyard is the Barbera vineyard, so the grape variety is Barbera. And as you can see, there are two types of inter-row management. One is grassed, in which we have just some mowing during the season, and the other is tilled. So we have mowing, but also we have tillage operation. And this was the perfect solution to test our inter-row grass growth model. So the data we got from this vineyard was data about grass, especially biomass, grass biomass. Here is tons dry matter hectare, but we convert in gram dry matter per square meter because it's the unit in which the model simulate. The cover, and the cover was estimating from the colleagues using this frame. This frame has this little frame in which they assign a number from 0 to 5. 5, of course, is the higher cover of grass. And as you can see, the cover can be not only green grass, but also Senesian grass, is the grass present in the frame. So they assign one value for each frame, and they define the grass cover. Then we have some information about soil water content that we convert into our variable, which is fractional transpirable soil water that you saw before. So an index from 0 to 1 to define the water stress. And then we have some information about the vine, so the pruning shoot weight, and the fruit biomass. In this case, we have fresh biomass, and we convert using a static coefficient into dry matter. This is the period in which we performed the study, 2021, 2022. And these are some results. Before to show you some results, I want just to say something, because the model is able to simulate green biomass. This means, sorry, so the model simulated the green biomass. So this is why we rescale the original biomass that was total biomass, including Senesians and green biomass. So we rescale the image, the picture they took in the field using a green index. So we mask the image and we extract the green index, and we use this index to rescale the original value of total biomass. So in this case, we obtain the green biomass. And we compare our simulation with this new observation. So these are the results currently we have for inter-row grass growth. So it's quite good simulation considering is a grass and it's quite variable across the season. And we have also some performances about pruning weight. In this case, also we simulate fruit biomass. There are data that I will not show today, but also we have the simulation of fractional transpirable soil water. In this case, the data derive from tilled and from grassed interrows, from both. So the idea in this case is to simulate the trend of grass and vine in future. So we use 3 SSP scenarios, 2.6, 4.5, and 8.5, and we compare this simulation with the present. So currently, I'll show you just the most extreme scenarios, so SSP 5, 8.5. So what we notice is that the development of the grass occur earlier during the season because of the effect of CO2, which increase in future. And of course, because in spring, probably there will be optimal condition, still optimal condition of water and temperature, while we have no no mowing during the summer, in which it's too dry and the level we cut the grass is higher than what we found in the simulation. So from a grapevine model to a vineyard model, again, we want to implement our solution, trying to simulate the carbon and water fluxes. And why? Why we want to do that? Because, as you probably know, agriculture is one of the most emitting sector, most emitting human activity. So not only regarding CO2, but especially regarding other non-CO2 gases like methane or nitrous oxide, which are very important. Currently, we are able just to simulate carbon, but we hope in future we will able to simulate nitrogen. And the CO2 is quite well simulated using some of models, biogeochemical models that you probably know, like the SENT, the NDC, that are solutions that already since a long time simulate carbon cycle. The problem to simulate other gases like methane or nitrous oxide is that they have a very high temporal variability and spatial heterogeneity. This means that it's not easy to measure the gas, and if it's not possible to have the measurement, it's not possible to simulate them, because we need data to simulate, to calibrate the model and to simulate. For the moment, the tools that we use to measure gases are tools that can be applied at micro scale, like gas flux chambers, automatic or not automatic, but gas flux chambers. Or at macro scale, we can use direct in the field the eddy covariance tower. These tools is able to simulate the gas exchange, not only the gas, so not only the mass, but also the energy between the vegetation layer and the atmosphere. Through the eddy, is able to simulate the gas. Depend on the tool that is on the gas analyzer that is on the eddy covariance, is possible to measure also methane and nitrous oxide. But in terms of simulation, in terms of prediction, the only way is to use biogeochemical model or use crop models that are adapted to simulate biogeochemical cycle. Of course, the carbon cycle, the water cycle, the nitrogen cycle is affected by many things, by soil, by climate, by management practices. So this is why we need to implement and to sometimes remodulate the solution to estimate the fluxes. And what we have done in our group is to adapt an original version of this model, which is a grassland model. The original version was VSTOC model published by Bellini et al. In 2023. This model at the beginning, in the original solution, simulated the grassland growth, so the biomass, using leaf area index, which was derived by Sentinel. So it was forced with leaf area index used to calculate intercepted radiation, photosynthesis, and then biomass accumulation. Now, the new solution has the possibility to use this original approach, or to simulate leaf area index based on temperature and based on weather condition. Then we have to change the photosynthesis approach, because the photosynthesis was originally net photosynthesis, the variable which was estimated. Now we start to simulate gross photosynthesis, so gross primary production, because we need to account for plant respiration. So we estimate gross primary production using a gross radiation use efficiency. Then we estimate plant respiration, and then we obtain our potential, we extract, of course, the respiration, and we obtain the potential biomass. Then this potential biomass is reduced with the effect of water stress. For example, we have also a thermal stress that account for suboptimal temperature that can affect photosynthesis, and so on. And then we have this coupling with ROT-C. ROT-C means Rothamsted C model, so carbon model. Rothamsted, probably you know, is a research unit in the UK, in which they developed this model using a long-term experiment of many crops, in which they were able to estimate and to define the decomposition rate, which are very stable because they are tested on long time and on many crops. So in this case, our senescent biomass is provided daily to the soil, and this it is decomposed in the active pool of ROT-C. One pool is decomposable, so it decomposes very fast the biomass. Other are resistant, biological, or humified, and so on. And the last pool, last pool is inert pool, so it doesn't change during time. We adapted this solution, changing the simulation steps, because at the beginning, ROT-C simulate at monthly time step. Now it simulates at daily time step to be coupled with our solution. Okay, these are the results we obtained from the grassland we simulate. On the left, you have the water stress, fractional transpirable soil water. The first grassland is ET Tor. Tor means Tornion, is the name of the grassland and the location that is located at 2,000 meters in alpine chain. Is a semi-natural grassland and is unmanaged. While we have Neuspit, is an Austrian grassland at 1,000 meters. The height is lower than the first, and is managed grassland with mowing, if I'm not wrong, and also located in the alpine chain. And then we have Borgo San Lorenzo is another site close here, so a Mediterranean grassland, and you can see very big difference in fractional transpirable soil water because we have very different condition, okay, among alpine area and Mediterranean site. On the right, we have the fluxes in terms of carbon fluxes. You have here the gross primary production for different sites, other grassland also are included. The gross primary production, which is defined with these three lines, because the black line is the present condition in which we have no increase of temperature, no decrease of precipitation, and the CO2 concentration as defined for the current period. The blue line is an increase of +2 degrees and a decrease of -10% of precipitation and stable CO2. So the CO2 is the same as in the present, while the red line is an increase of +2 degrees in temperature, minus decrease, so a decrease in -10% in precipitation, and an increase of CO2 concentration as defined for RCP 8.5 scenarios. So what we can see here is, as I show you before for the interrow, we have an early occurrence, an early development of gross primary production at the beginning of the season because of the fertilization effect of CO2 when temperature and water condition are optimal. Then it decreases during the season. And the RECO, the ecosystem respiration, which include the soil respiration and the plant respiration, is higher during summer, of course, because in this case, when we simulate, especially when ROT-C simulate soil respiration, it accounts for temperature and water stress effect. So this means that soil respiration with high temperature in summer can increase, of course, this until a limit, of course, a cutoff temperature. The last column is evapotranspiration, is a water flux, but the first column is the net ecosystem exchange. So is the ecosystem respiration minus gross primary production. And net ecosystem exchange is 0 when we have no exchange. is negative when we have a carbon uptake, because we have gross primary production higher than ecosystem respiration, and is positive when we have emission from the system, so carbon is emitted into the atmosphere. In this case, ecosystem respiration is higher than gross primary production. So we are trying to do in the same as I told at the beginning, and we are trying to adapt our solution, vineyard solution, to simulate also the carbon fluxes. I want to just say that we are currently use ROT-C, but because ROT-C is very simple solution in some way, if we can say like that, but it require a few inputs. So for us, it was a good option to use. But we are also evaluating other possibilities to change the carbon model or to introduce, again, another alternative and to allow the user to choose. So you saw already this slide. So we are trying also to modify the different partitioning, because we account for the respiration in terms of growth respiration and maintenance respiration for each one of the organs. So for us at the moment is not too easy to do that, because you have to imagine we need data to test each one of these respiration, this simulated respiration. So we are trying to adapt with the final output we have, that in general are the carbon fluxes at macro scale level, because we have in our vineyard here in Tuscany an eddy covariance we are monitoring, and we are getting data from the vineyard. So we are trying to then adapt the model to simulate in a Mediterranean environment. So what the model is doing now is to provide carbon input to ROT-C. This carbon input is provided daily, so a fraction that daily arrive to the soil, and daily is decomposed into the soil. And these are the results. So what you saw before, the net ecosystem exchange and the trend, these are two management, because we have the C inputs from vine, we have the C inputs from grass, both, that are decomposed with different CN ratio, because shoot, of course, is characterized by different components, more resistant components compared to grass, that easy to decompose in the soil. So we adapt also this parameter. So in this case, the system is emitting into the atmosphere. This spike, we explain this spike because for maintenance respiration in plant, in vine organs, we use a simulation approach. We take into account the temperature, and when we are in summer, this temperature overcome the threshold, and this situation makes that we have this spike in the respiration of the plant. So we are trying to understand how to limit this or to adapt this respiration, this maintenance respiration, maybe changing the threshold that we currently got from literature. In this case, at the beginning of the season, we are uptaking carbon. So carbon is stock in the soil and a stock in the perennial organ of the vine, also in the grass, but the grass, it decomposes quite fast, so it remains on the soil for a few times, so we trust more in perennial organ of vine. So basically these are the new implementation we are trying to adapt for our models. So summarizing the conclusion, crop models can be useful tool, as you can see in many agricultural applications, And in digital agriculture, the integration of crop models in appropriate digital support system, as also Nicolò said before, plays a major role for optimizing farm management, maximizing production. That is indeed the aim of precision agriculture, reducing the waste of resources and reducing the impact on the environment. For reducing the impact on the environment, we need tools that are able to assess the environmental impact and to assess correctly, as close to the reality as possible, the effect and the impact on the environment. So here are some suggestions for you. If you want to read something about modeling, I start from the last. The last is a book of Soltani and Sinclair. This book is quite good because they show how to build a model. They build this model for many cereals and many crops, and they provide the code and also show step by step how the plant nitrogen budget, for example, or soil nitrogen budget or water balance are connected to affect the plant growth. Then the other two, especially Nendel, 2023, also we participate to the writing of this book, is about modeling climate change impacts on agricultural system and in different also regions in the world. And it's quite good for showing the current solution of modeling that are used worldwide. And the first one is more related to precision agriculture, but also with some aspect related to modeling, and it was published in the same year. And the first author was Davide Cammarano. And let me finally give you some communication. This is the special issue is currently open on Italian Journal of Agronomy, and the topic is perfectly fit with this summer school, that is digital agriculture to mitigate greenhouse gases emission. Is open until the end of July. But probably it will be extended. And the topic for the special issue are modeling, basically, modeling the greenhouse gases emission, precision agriculture, how to use precision agriculture to mitigate greenhouse gases emission, and methodology that currently are used to assess the environmental impact and to assess the the fluxes and the emissions. So it's time to wake up, I think, for you. I hope I've bored enough today. So thank you very much.
Lisa, thank you very much for your presentation. I think we can move forward with questions if any of the present public have any, please. Then I would have a very short question. You've mentioned during your presentation that large computational efforts may be one of the downsides of the crop models. So my question would be, in case that we have too many simulations, would you actually expect this to happen very often, sort of a break of this model? And are there any ideas to maybe overcome this in the future? Thank you.
Okay, it depends of many things. Depend, as I told, of the complexity of the model you want to simulate, of the software language, because, for example, in the course I took on Stix is much more complicated model than what we use in our group, and it works in Java Stix, and it's quite fast to simulate. So it depends to many things. But this depends also how you organize your code and how to run the model. So I don't think it's a big problem now. It was maybe much more in the past, but still, if you need to perform many simulations, you have to take into account that probably you have to increase the performance of your solution.
Great, thank you. Thank you very much for your answer and for the presentation again. To the rest of the public, I would like to invite you, sorry? Yes, once again, of course, thank you. I would like to invite you for a coffee break in the student club, and please be prompt at 12:15 because our next speaker is scheduled for then. Thank you. Okay, I think we can continue with the presentations. Our next speaker is Christoph Menz from Potsdam Institute for Climate Impact Research with his titled presentation, Introduction to the Phenology Modeling Framework.
Okay. Now? Okay, so hopefully everybody can hear me. So hello everybody, it's me again. I would like to continue my endeavor that I started yesterday on climate change impacts on Montenegro. However, these times I will be introducing you to more practical results, practical for farmers, for wine growers, than the results or the impacts that I showed yesterday. And my presentation fits quite nicely into the presentation that Luisa showed previously, because Luisa introduced you to crop models. Most of the crop models are process-based models. And so they are basically a collection of submodels simulating separate processes like soil processes, biomass accumulation, respiration of the plant. And I will focus here on one specific process, and this is phenology modeling. And specifically, I would like to introduce you into one phenology model that I have developed. Well, not model, but framework for modeling phenology. Okay, so first a quick overview. What I would like to show you is I will first revisit the things that we end up yesterday with, so the climate change impacts specifically on agriculture for Montenegro. Then I would like to introduce you into what plant phenology actually is. Then how we model this plant phenology in general from a theoretical point of view. And then I will continue introducing you into the modeling framework that I've developed and show you some results from sensitivity studies with these models and also application of this model for future projections for Montenegro. All these simulations that I would show you are really, really preliminary. So they are, the model is still under development. So take all the results with caution. Yeah. Okay. Okay, so start with climate change impacts on agriculture, specifically for the Montenegro. What I showed you yesterday is, for example, the number of frost days in the future here for the spring period for the end of this century, so 2100. And what we saw there is that we have, in terms of spring frosts, very good future projections for agriculture. So we have in general, even in the green future scenario, so with low greenhouse gas emissions, we will have nearly no frost events that can damage crops in the future in Montenegro. And this even goes into the mountainous regions of Montenegro. What I also showed you is the growing season length that showed also favorable conditions in the future. So we have an extended growing season length and therefore a possibility to have multiple harvests, multiple plantings in a year for Montenegro. And I also showed you the Huglon index, which basically tells us that for Montenegro in the future, we will have more and more areas that are suitable to grow wine, and also more and more areas that are suitable to grow high quality wine, so high quality red wine. However, if you're a farmer, these informations that I provided yesterday are not so practical. These informations are more practical for stakeholders and policymakers to get this general overview. But if you're a farmer, you're not interested in things like growing season lengths. If this increases or decreases, what as a farmer, you might be more interested in what is a crop that I can grow there in the future. So is it maize? Is it wheat? Is it wine? Or and also when should I plant it? So these indicators like growing season lengths are not so practical to use for farmers. To end up with more practical results for farmers, we use usually what is called climate impact models. And the crop models, for example, are one of these climate impact models. So really models that simulate the future impacts of climate change in much more detail and in a detail that are really practical to use for the farmers. So for example, telling the farmer when is the ideal planting date in the future? What is the ideal plant and the cycle of the plants that you should use in the future if you would like to have multiple harvests. And here, as I said, I would focus on one specific process or one specific aspects of climate change impact models, and these are plant phenology models. And as the pictures here already tell you, this is not generally plant phenology. I would like to focus here on plant phenology for a specific plant, and this is wine, so grape wine. Okay, so first some, again, basic concept to introduce. So in many presentations you hear before that they simulate plant phenology. However, I would like to introduce you first here to what plant phenology actually is. And plant phenology is basically the study of periodic events in the plant life cycle. So how the plant develops throughout the year, from bud break to leaf development to flower development, then development of the fruits, ripening of the fruits, and then going back, losing the leaves and going to dormancy period. So this is really what is called plant phenology. And as I said, I would like to focus on wine phenology, so the phenology development of wine. And why this is important, it is because wine phenology influences the yield, so the amount of yield from wine and also the quality of the wine that we have after, or that we can achieve after harvest. Then the weather conditions drive, of course, these phenological developments, and I would like to explain you in the next slides how this works. So we have always this interference of weather and plant phenology that makes it important. Then extreme events like frost events or extreme rain or hailstorms can damage the crop, but they can damage the crop only if they are in a specific status. So if the wine is in dormancy, for example, a frost event will not cause any damage to the plant. But if the plant is already in a later development state, if it already develops leaves or flowers, a frost event can damage really the plant or the wine. So that's why phenology is also important in context of extreme events and the impact of extreme events on the agriculture. And yeah, as we are all talking about climate change will also have an important impact on the crop phenology. What we saw in the previous presentations, like shifting the phenological cycle when bud break occurs, or how long the ripening period is in the future. So this is affected then by climate change. Okay, so before going to the actual modeling of plant phenology, what we need in terms of modeling is some quantification. So how will we quantify the phenological development? So you hear a lot about phrases like bud break, flower development, leaf development, ripening period, maturity. To model these aspects, we need to quantify these aspects in a certain way. So we need to correlate these names to specific numerical values to put them into the models and then actually simulate them. And this is already done in 1989, so at the end of the last century. And the quantification measure that was established is the so-called BBCH code. This is something that already was explained to you a bit by Daniel in the yesterday presentation. So he showed you how he modeled several BBCH stages, and I would like to introduce you here to in a more detailed into this code definition. So BBCH is an abbreviation for German couple of German institutes. So the long name BBCH is Biologische Bundesanstalt, Bundessortenamt und Chemische Industrie. So this is just a collection of the institutes, both from the industry but also from the ministry that developed this code. And they were funded, or this research was funded by 4 main funders from the German industry, and this is the chemical and pharmaceutical companies Bayer, BASF, Ciba, and Höchst. And just by coincidence, if you take the first letters of these companies, you also end up at BBCH. But this is probably just a coincidence. At least the companies tell that they are not responsible for the name. So the BBCH was necessary because we need to quantify the phenological development. Why do we need to quantify the phenology development? For our purposes to model, but there are also other needs why we need a unified code to define phenology development. And this is, for example, to synchronize field trails. So to compare the experiments we have on different fields. Then, of course, to monitor the climate change impacts, like we will do at the end of the presentation, like showing how a specific phenological phase will advance or get shorter in the future under climate change. And for the farmer themselves, these BBCH stages are important because they can be used to determine the dates when they need to apply fertilizer or pesticides. The BBCH stage, the BBCH code, is a 2-digit code, and you have the first digit that basically tells you the phase development. So in which phase the crop actually is, and the second digit tells you then the sub-development in this phase. So as an example here, this is the BBCH code table for wine phenology. So every BBCH stage that starts with a 0, so the first digit is a 0, is about the bud development or sprouting. And there you have, for example, the subcode BBCH09, which is the code to indicate this is bud break. Then we have every BBCH code that starts with the 1 is for the leaf development. And there you have, for example, the 1-1, the code 1-1 is we have developed, or the plant has developed the first leaf. 1-2 means it develops the second leaf, 1-3, the third leaf, and so on until 1-9. Then we have every BBCH code that is starting with a 5 is for the inflorescence. And the inflorescence is basically the part of the body of the plant that is responsible for developing the flowers in the future, or in the development cycle. Then every BBCH stage that starts with a 6 is for flowering, so developing really flowers on the inflorescence. Every BBCH code that starts with a 7 is for fruit development, and every BBCH stage that starts with an 8 is for the ripening phase of the wine phenology. One thing I like to mention is that this table that you just showed, you just saw, is for wine phenology. But there are other tables or similar tables for any other crop you can think of. So they are because every crop or every plant has a slightly different phenology and different stages. So there are BBCH stages for wheat, for maize, for chestnut, peanuts, strawberries, and each of these plants has slightly different BBCH stages. Okay, so now we have a quantification of phenology. We can relate a certain phenology stage to a certain number in the BBCH code. The question is, how will we model this? And the first thing I would like to motivate is the variables that we use to model phenology. And what came quite often in the last presentations is that we use temperature to model the plant development. This is quite natural choice to simulate plant phenology with temperature. And the reason for this is or there are a multitude of reasons why to do this. One important reason is that the plant development is basically based on chemical reactions, so like photosynthesis and the respiration. And these chemical reactions that are taking place are, of course, more efficient on a specific temperature range. So that's why temperature is important for the development. Then the water and nutrient uptake by the roots is also optimal under certain, from the soils, also more efficient under specific temperature ranges. And you can think, for example, of stresses that are temperature related, heat or cold stress that can reduce the development of the plant. So if you have freezing temperature, the water freezes and the plant cannot take up the water and cannot develop. So there also temperature has an important impact on these development aspects. And one thing that most of the models or all of the models are used is not the direct temperature, but temperature accumulations. This is also quite intuitive because the whole plant phenological development is an accumulative process. So the plant over the development stages of the year accumulates biomass, increases the number of leaves, increases the number or accumulates the number of leaves, accumulates the number of flowers, and so on. So this is the phenological development itself is an accumulated process. So it makes sense to use accumulations of temperature to model it. And to give you an example how how strong our temperatures and the BBCH stages are related, I plotted here over 1 year, from the day of the year 100 to, so basically the start, slightly before the development starts, to a couple of days after the development finishes. So after the day 300, I plotted here the accumulated temperature here. And up here, the BBCH stage that we are in. So here you have BBCH stage 25, 50, and 75, for example. You see how the BBCH stages changes in time, and you see here how the temperature accumulates throughout the year. And on the bottom here, you can see, or first, each of these lines here is one specific year. Okay, so we have here 60 different years, 60 years of BBCH measurements, and 60 years of temperature measurements. And then on the bottom here, I simply collected the accumulated temperature at a specific BBCH stage that was observed. So if we could use temperature perfectly, just to model the BBCH stages, everything should line up on this line. And you can see that they do not quite end up at the 1-1 line. But they are close. So we need to make some adaptations to our models. However, we already see that there's quite a strong correlation between the accumulated temperature and the BBCH stage. And we can do the same thing for other variables. And here I just plotted the same plot with minimum temperature, average temperature, as we saw before, maximum temperature, solar radiation, wind speed, relative humidity, sunshine duration, and precipitation, just to identify maybe variables that can also have an impact on phenological development or on the specific BBCH stages. And what we can see is that we have, at least for the temperature values, we have a small variability. They all do not end up quite well at the 1-1 line, so we cannot use them directly, but the variability is quite small, so there is some correlation for the minimum temperature, maximum temperature, and also solar radiation. So we can guess that these are also variables that we can use for phenological development. While for other variables like wind speed, we have quite a long range on wind speed accumulations that represent a specific BBCH stage. So there's a smaller correlation between these variables and the BBCH stage. Relative humidity is also not so good. Sunshine duration and precipitation are also not such good variables to simulate the whole phenological cycle. However, we can guess, for example, for precipitation that there should be no immediate response of the plant to precipitation, but maybe a lagged response. And there's also influence of the soil water, that because the plant not just take the precipitation water, but also the water that is in the soil. And this makes the correlation between precipitation and the plant development quite difficult. Okay, so in general, it seems like the accumulated temperature seems to be the best variable that we can choose to model plant phenology. And this is what we could already guess just by remembering the Huglin scale or the Huglin index. The Huglin index itself is already a temperature accumulation. So we accumulate temperature over a specific period of time. And then we have at the end the specific heat sum, so a daily sum of heat. And this heat sum basically tells us then what is the suitable variety that we can plant there. And the idea in terms of phenological development is that for certain varieties, we have over the year enough heat to end up at the end of the phenological cycle. So for some plants, like white wines, we need less heat to end up at the ripening phase. So we accumulate less heat, or we need to accumulate less heat. So we end up at lower Huglot index values. While for white wines, we need more heat to end up at the latest phenological phase to fulfill the phenological cycle. And that's why they end up at a higher Huglot index. So the Huglot index you can think of as already a phenological model. Okay, so how do we actually model phenological development? And one of the first models that I used to simulate phenological development was designed by Réaumur, a French physicist that besides developing these models also develops a scale for measuring temperatures. 10 years before Celsius develops his degree Celsius scale. So how does this model look like? So here you have the where's my mouse? There's the mouse. Okay. So here we have the equation that he has developed. Basically, what he designed here is that we have a sum that starts at a specific date of the year, and it ends at a specific date of the year, like, for example, going from the 1st of April to the 30th of September, like the Huglot index. And then we have accumulated a temperature difference. This temperature difference is called a degree day. And this is simply the temperature that we measure at a specific day minus a base temperature, or what Daniel called the threshold temperature. And we basically accumulate over these dates here, over all these days, the temperature difference that is also above this temperature base. So we don't accumulate here negative temperatures. So we only consider temperatures to accumulate that are above these T base, the base temperature. And then this sum in total will be something like what is called here S, so an accumulated number. And this accumulated number can be then related to the end of the phase. So at the end, while modeling, what we prescribe is usually not this ending date, but we prescribe a sum that needs to be reached to end up this phenology development. So we basically sum this to infinity, if you think, and then if we reach a specific accumulated threshold, we say this phenological cycle has ended, and we can just read the end date. Okay, so the three model parameters of this simple model are just the starting date. So when we start the accumulation, the base temperature or temperature threshold, and the accumulation threshold. And then from the accumulation threshold, as I told you, we can just read the ending date of the phenological development. One thing I would like to mention is that this model was developed for plant phenology. However, the same concepts can be used to model also other processes in the biological system. So like, for example, animals or here insects, invasive species. So the habitat of a specific species can be also modeled by accumulating temperature. So this basic concept of just accumulating temperatures over the year or over a specific time period is kind of powerful also to model other aspects of the biological system. Okay, so we have the Reaumur model. However, and it works, but we can improve this model. And we can improve this model in two regards. And one is instead of simulating, like in the Huguelot index, the whole year from the 1st of April to the 30th of September, we will divide, like in the BBCH code, the phenological development into specific phases, like, for example, the sprouting or bud breaking phase, leaf development, inflorescence, flowering, fruit development, ripening, and dormancy period. So we divided the development into these phases, and then we simulate with a Reaumur model every single phase separately. So this is one modification that we can make to improve the simulation of our model, and that this is quite a good idea. You can see here on the right-hand side, this is again the day of the year for the development. Each line is one specific year. And on the left-hand side, you can see the BBCH. And you can see that after specific, or that the development of BBCH as a straight line is depending or is different for different phases. So here in the leaf development and inflorescence and flowering period, we have a quite inclined linear increase. And then for the fruit development, it seems to slow down. Okay, so it makes sense to divide the whole calculations of the model into different phases. The other improvement that was done to make better simulations with phenology models is, instead of using this temperature difference, what we called degree days, we can also define more complex functions of temperature, for example. So this means that for the Reaumur model, we had the sum of the simple temperature difference, but with more advanced models, we interchange this temperature difference with some more complex function of temperature. And we call these functions then response function, because this is basically telling us how the plant responded to a specific temperature input. That's why we call them response functions. Okay, so going from the simple Reaumur model here, what is the model that we end up with these two modifications? We end up with basically this kind of model, so where we have, again, a sum, but this time the sum goes only for a specific phase, for the starting time of the phase to the ending time of this phase. So like, for example, for the flowering phase. And then we calculate, instead of the temperature difference, we calculate for each phase a specific response function. And we end up at a specific accumulation threshold that is also specific for every phase. So instead of having now one model that simulates the whole phenological cycle, we have like 5 smaller models, each model which is own parameters that simulates the single phenological phases, and these models build on each other. So the starting phase of the inflorescence for example, starts at the end of the leaf development, for example, or the fruit development phase starts at the end of the flowering phase. So that's a quite natural combination or consecutive order of this model. Okay, so the three parameters of this model, of this concept of model, are now more, or we have more three parameters. Still, we have the start of the phase, and we have the accumulation for each phase. But then we also have not a single free parameter, but basically a couple of parameters depending on the response function. So we can choose different response functions and each response function has a specific number of parameters. So this just enlarges then the complexity of the whole modeling approach. Okay, so what kind of response functions do we usually use for the simulation of phenology phases? I divided here the response functions into 3 different classes, and I would like to just show you what the different response functions look like. So I would start with quite simple response functions that has only one development threshold. So like this base threshold in the Reaumur model. And here, like this. Okay. Here we have how you can see how this model or this response function look like. We have here on the x-axis, we have the temperature from cold temperature to warm temperatures. The exact value doesn't interest here because we just want to see the general behavior of this response function. And on the y-axis, we have the growing degrees. So what is the value of this response function that will then be accumulated? And for the simple Reaumur model, we have until a specific development threshold temperature, we don't have any development. And then after that, we basically have a linear development. So the higher the temperature is above this threshold, the stronger the influence of the response is. So the stronger the development or the faster the development is. If you are familiar with neural network, you know you might recognize that this function is basically the rectified linear unit that is used in neural network activations. It's quite interesting because also all the other simple response functions that are used can be also or are also used in neural networks. So for example, we have the sigmoid function that is quite heavily used as a response function in the phenological development. And the idea basically behind using the sigmoid function is that here for the Reaumur model, we have quite a strong discontinuity. So we say until a specific threshold, we don't have any development. And after that, we have a linear development. However, the sigmoid function basically tells us that the development might also start earlier before the threshold, but very, very small. Then it increases until a specific threshold. And then it saturates to the most ideal or most possible development. So it's basically smoothing the strong discontinuity of the Reaumur model. And then there exists also other variants. So for example, the hyperbolic tangent, which has also similar properties, and generalized logistic function that is also used in neural network. And then we have one specific type of response functions that was previously not used. But since we have so much analogy to the activation functions from neural networks, I thought that maybe it's also a good idea to take from the neural network research some activation functions and test them in the modeling framework. So recently, more models use this PLO function that is parametric exponential linear unit. And that makes sense to use this as a response function for phenology development, because this function basically is similar to the Reaumur model, but below the development threshold, we have basically an exponential growth for the impact of temperature on the response value. So we don't have such a strong discontinuity, and we have some small development below the threshold, which is quite intuitive or naturally that this will occur. Then the second class of response functions are response functions that has more than one parameter. And there we have, for example, the quite famous Richardson model. And this model has two development thresholds, one lower threshold. Below the threshold, we don't have any response. Above this threshold, we have a certain response until we reach a specific upper threshold. And after this upper threshold, we don't get any stronger response from higher temperatures. So it basically saturates the response on high temperature. Then we have the model UniFen that Daniel yesterday introduced. And this is basically an extension of the Richardson model. And it introduced another threshold on the very, very hot end of temperature. And the idea between why this is implemented is because you can think of that under very high temperature, the plant is under stress and it reduces respiration, or it just quits respiration. So we have a reduced development under high temperature. So, and then we have again more smooth versions of this. So like the double sigmoid, which is again similar to the UniFen model, but we don't have discontinuities. We have a smooth graph. So it has probably better properties and might better represent the actual behavior, because we can think that we don't have fixed temperature thresholds. We might have a boundary of thresholds, you can think. And we can also have some models like the Wang model, where you can basically tweak how steep the incline and decline is after the threshold. And we have even more complex models. And these complex models has either the property that they use multiple thresholds, multiple variables to simulate phenological development, so not just temperature. And there are also models like, for example, the Sing model for phenology development, which is not using daily temperatures, it uses hourly temperatures. And since we don't measure usually, or in most cases, we don't have measurements of hourly temperatures, this model estimates the daily temperature cycle by using the minimum and maximum temperature of this day, and then approximating these as a sine curve, like you see here. And then this model simply uses on these hourly temperature values such kind of response function, which has a lower threshold and an upper threshold. And after this upper threshold, we have a decline of response. Then we have, you can think of an extension of this sine curve and response function application in a class of model that were first introduced by Ellen. And this basically also used a sine curve to approximate the daily cycle of temperature. But then instead of having these upper and lower threshold, it integrates the area of the sine curve between the lower and the upper threshold and use these then as a value that can accumulate over the whole phenological cycle. And there are also models that integrate this daily cycle approximation. And on top of that, they also use multiple variables, like, for example, the model from Hoppmann and Berkelmann-Lönertz, which to simulate the ripening phase, also not just use the temperature, but it also uses the radiation and the precipitation, and each with different response functions. And it also uses the an accumulative factor of the days that the plant is in a specific phase, because there they say that there is a specific pressure for the plant that the longer the phase will last, the faster it will end, basically. Okay, so these are the models we use to simulate the phenological development. However, we have one elephant in the room that we have not discussed yet, and this is we have some starting point of the phenological development. So in the year, the phenological development has to start at a certain point, and usually we don't know this point. So there are some practical ideas how to deal with this. But first, I would like to introduce you into the problem in general. Okay, so what are the biological sources or grounds for the starting of the phenology development? So the problem is that we need, at least for the very first year, for the very first phase that we would like to simulate, we need the starting date. Okay, and usually in biology, we know that the plant, or at least perennial plants, start in dormancy. So at the end of the year, the plant goes into dormancy, and at the beginning of the year, they came out of the dormancy and start their development. And the question is, when does they came out of the dormancy period? And usually it goes under 3 different phases. So first we have the dormancy entry phase. This is basically at the end of the year, the days gets shorter and it gets colder. So the plant removes its leaves. Okay, this is called the dormancy entry. And then we have a specific phase that also, or 2 phases that Luisa also mentioned, and this is the endodormancy and the ecodormancy. The endodormancy is kind of a complicated thing, because this is just a period that is a cold period in winter that is required by the plant to know, okay, there's winter. I already stopped the development, and it is cold enough so I know it is winter, and I can initiate in the future my further development. So this is basically just a period where the plant needs cold temperature to know there's winter and I can continue my development when it gets warmer. So this is the endodormancy period, and then we have the ecodormancy period that is usually in spring, and there we still have cold and dry temperatures, cold temperatures or dry conditions. So the plant sees that I cannot start the development. However, I have finished the endodormancy period, so I can potentially continue my development. Okay, and phenologically, it is hard to measure these phases, so we cannot really measure the endodormancy and the ecodormancy period because there's no visible development in the plant. What we can observe is the starting of the development after the ecodormancy period. So when it gets warm again, we can then measure how the buds are swelling on the plant. Okay, so how do we deal with this initialization problem? So there are basically two practical ways that we deal with this. And one practical way that is used most often is the pragmatic approach. We just ignore the dormancy period. We start the model on the 1st of January, and then we start with simulating the bud break phase. This is quite a crude approximation because we ignore basically the whole dormancy period. However, in practice, it does not make such a big mistake on the phenological development of the first phase. The bud break phase is still simulated quite good, even though that we ignore the dormancy period. The other approach, and this is something that also Luisa talked about, is, or first, this pragmatic approach is usually called the forcing approach because we just start with a prescribed value and then we force the development with heat. The other approach is the so-called chilling forcing model or chilling forcing approach, where we first have this cold accumulation to go into endodormancy and ecodormancy. And then we can simulate from the end of the endodormancy period the sprouting. Usually these models can be initiated also on a specific day, like but in the previous year. So we start these models in the previous year and then simulating from the previous year the go into the winter and the dormancy period. But we can also say that we initiate these models at the end of the development cycle of the previous year. So after the ripening phase or after the harvest, we can just say, okay, now the model should simulate the dormancy period or try to go into dormancy period. Okay, so continue. Now we know the basic concepts that are used to simulate the phenological development. And now I would like to introduce you into the modeling framework that I have developed. And I thought that that might be a good idea because I think most of you are coming from computer scientists or mathematics. So you are familiar with programming. So I can show you at least pieces of code here. Okay. Okay, the basic idea behind the phenological modeling framework is to collect all these different response functions and then put them into one model framework. So what is this framework about? This is a framework that simulates the phenological development of plants. Initially, it was developed just for wine, but as we have a large number of phenological response functions, you can also use it for other plants. It is based on the very first Reaumur approach that we accumulate temperatures or response values over the year. Yeah, so the model is intended to be quite flexible. So the idea is that the user can decide what is the phenological phase I would like to simulate, how are the phenological phases orchestrated over the year, so how is the consecutive flow from one phase to the other. And also in the latest version, I implemented this, not just the forcing approach, but also this chilling forcing approach. So the model is also able to simulate the dormancy period. What is it intended for, or for which person it's intended? So right now it's just intended for researchers. So we don't have a flashy graphical user interface. You need a console. You need to know programming in Python because it's programmed in Python. It is intended to study the impact of climate change. So that was the initial goal, that I have a model I can use in climate impact modeling. And it's also intended to be as simple as possible with having enough interfaces or the suitable interfaces to integrate this model into larger crop models. So as you saw in the presentation of Luisa, phenology is just one sub-process that is used in larger crop models. Okay, so some features of the model. It's programmed in Python 3. It only uses 2 modules of Python, and this is the NumPy and the Pandas module. The data that it uses is the Pandas data frame. It needs daily climate input data. The output of the model are for each day of the year the specific BBCH value. So the phenological code, or the BBCH code for the specific phenological development stage. Then it is quite flexible to orchestrate different phases, or having simulate the whole year as just one phase, for example. So you're quite flexible how you design this model. Each phase itself is defined by a specific BBCH range, and then we have some kind of linear interpolation to get for the specific phase also the second digit value, basically, for the BBCH phase, for the BBCH code. I designed it to be quite extensible. So right now I have integrated 17 different response functions, but the design of these response function is as simple enough as even a not trained programmer can integrate a new phenological response function. And on the downside, right now it's still in testing, so we have restricted access right now just for colleagues that work on the PIK and have access to our GitLab. The model in total is quite small. So in general, the main routines are just 483 lines of code, which is very, very low number of codes, considering what most of other climate impact models present. And most of the lines come from the 17 different response functions. Which response functions are implemented? I, again, here as a divided into the different classes. So we have the single threshold function, the degree day approach, or the Reamour or ReLU approach for response function. Then we have the parameterized exponential linear unit, sigmoid, generalized logistic, and hyperbolic Tangang for this class. We have multiple threshold functions, the double sigmoid, squared sigmoid, which is quite similar to the double sigmoid, so it's just the other functional expression, but has similar properties. Then we have the Richardson model, the Unifen model of Daniel, and the Wang model. And for complex functions, we have 2 approaches that are usually used not for wine, but for modeling the phenological development of rice. But they also work quite well in the context of wine, and they simulate the daily cycle. And then we have also a model that was developed, as I said, from Hopman and Beckerman-Lönnertz. Yeah, right. So what's the basic modeling concept that the whole phenological modeling framework is using? So on top we define a phenological model. And this phenological model is then basically an orchestration of phenological phases. Okay, so we have here one phenological phase, then after that we have the second, the third, and the fourth. So you can think, for example, this models butt break, this models the inflorescence, this models then the second should model the leaf development, then we model the inflorescence, then we model the flower development, and so on. So we have just an orchestration of consecutive phenological phases, and each phenological phase has a specific response function that it used to accumulate enough heat or enough response to end this phase. Okay, so what are these specific contents of the whole model? And I will go now from the bottom, from the response functions to the phenology phases to the whole phenology model. So I go from bottom to up and start by the definition of one specific response function. Here, example, the Richardson response function. And this is just defined as a Python class. So it's an object at the end. And we have here the constructor definition of this class, and this just take basically the thresholds of this response function. For the Richardson model, it will be the lower threshold and the upper threshold, and then we have also a parameter that defines how steep is the incline from the lower response to, or from the lower threshold to the upper threshold. And so this is one method that is defined for this class. And the second that is important to define is the predict function or method of this class. And this just simply calculates the response of a specific date using this response function. So this is all we need to define a response function. We need the initialization, giving all the parameters that the function needs, and the predict function that calculates the response value for this response function. Yeah, the naming conventions are basically coming from another Python library, and this is the sklearn library, which basically defines the specific namings and functions of class modules for general machine learning. And the idea is here to use also then these sklearn modules to do, for example, the optimization procedure or the calibration procedure. That's why I followed here the same naming convention. So these other modules don't get confused and they don't need to do any namings afterwards. Then we have on top, we have the response function that is incorporated in the phase. And the phase is basically defined by the response function that it uses with the specific keywords. So what is the upper threshold? What is the lower threshold? And all that the phase module is doing, basically it calculates for each day, or it takes the temperature inputs for each day. It calculates then the response function for this for each day, and then it accumulates these over the whole phenological cycle. So everything that these phenological phase object is doing is accumulated. It's just calculating the sum from a given BBCH range. So we say, for example, that in the butt break phase, this phenological phase object should calculate from BBCH code 00 to 09. Okay, then this is all then integrated into the whole phenological model. And as I said, the phenological model is just the orchestration of different phenological phases. So it really just integrates into each other. Yeah, so, and the phenological model also handles then the calculation over multiple years. So it takes a time series of 50 years, for example, it divides the time series into each year, and then it executes the phenological phase development for each year separately. Okay. Now some code snippet how everything is then put together and run in a single Python script. So the first thing that we need to do is we read the climate data here using pandas module from Python. And this will define a pandas data frame. And this is, so to say, unified data frame. So every climate data, if you read it like this, will look the same. And this is also the look or the frame or the how it should look to present to the model. Then we define a sequence of phases. Okay, so each single phase that we would like to simulate each year in a consecutive order. In detail, these phase sequences look like this. So we define a phenological phase object, give it a specific name. Then we say this is a response function. In this case, the rectified linear unit response function that should be used to simulate this phase. Then we have we define the thresholds or the keywords for this response function. In this case, for the rectified linear unit, we define the lower temperature threshold. Then for the phase, we need to know when does this phase start, especially for the butt break phase, we need to know when it starts. One means it starts at the 1st of January, so it's defined in days of the year. 1st of January is the first day of the year. And then we define an accumulation threshold. So how far should the sum go until this phenological phase ends? So the phenological phase basically sums up this response function over the whole year and then identifies the day where this threshold is reached. And this day is then the end day of this phase. So it defines basically the end of the phase by this accumulation threshold. And then we can define that this specific phase, but development is representing the BBCH range from 0 to 9. And then after that, we give the next phenological phase. In this case, it's leaf development. Leaf development uses another response function with other keywords or other thresholds and other accumulation thresholds. And it also represents a different BBCH range. Okay, so this is all that you need to define for the phenological phases and for the phenological phase sequence. Then we can create with this phase sequence, we can create the whole phenological model and run the model. And that's all. And what we get at the end is like this. The input is a daily time series of minimum temperature, maximum temperature, average temperature, and precipitation in this case for each day of a specific date range. Then we need our specific phase sequence, put the climate input data and the phase sequence into the phenological model. And the output is then again a pandas data frame, but now added the BBCH values for each day of the year. Okay, so this is the basic output of the model. And that's all we need. So we have at the end, or we have on one hand side, we have a climate input, and on the output side, we know for each day of the year, what is the specific BBCH value that we have. And the BBCH values we can then, of course, relate to specific phenological development stages. And here you can see how the time series of the simulation looks like. So here we have over a period from 2006 to 2009, the simulated BBCH values of this model. Now, this is just to simply modeling the phenological development if you know all the parameters that you need to model. So if we know what is the starting day, what are the thresholds, what are the accumulations thresholds that we need to fulfill phenological development. But usually we don't know these. For each new site, we need to calibrate or determine these thresholds because each site might have a different plant, have a different soil conditions, have a different weather. So we need to calibrate our models. We need to estimate these thresholds. We need to estimate the accumulation thresholds. And for this, the phenological modeling framework already comes with a wrapper routine for calibrating your phenological model. And the idea behind this wrapper routine is to somehow rearrange the different namings and functions in the phenological model to get in line with the convention of usual optimization modules of Python. So in Python, you have a multitude of different optimization algorithms that can be used to calibrate a specific machine learning model. Usually it's only used for machine learning, but they have introduced certain contexts and naming conventions that are used by all these modules. So by following these conventions, I can use this modeling framework also in the context of all these optimization modules that are usually used in Python for calibrating machine learning models. So I simply translate the phenological model or phenology model to a machine learning model that can be then just treated as a machine learning model. And the basic concept here is that the whole model needs to have a function that predicts the phenological development, so creates a time series of phenological development, giving a specific vector x, and this vector is now the vector of parameters, so the thresholds, the accumulation thresholds, and the other function that is needed to implement them into these optimization function modules is a scoring function. So a function that takes basically observations and then calculates with the given parameter vector, how good or bad is my model? How close are we to the observations? Okay, then again, a short code snippet, how it looks like. So we have now the climate data, but to run the calibration, but we also need phenological observations. And both are again just read as Python data frames. Then we define an evaluation dictionary in Python. And this dictionary basically contains the phenological observations, so our reference data. It defines the metrics, so what is the scoring function that we use to calculate how close is our model simulations to the observations. And then we need to define the BBCH list. So what BBCH stages should be compared between the simulation and the observations? Because the simulation, you get a time series of all the BBCH codes, but in the observations, you usually has just BBCH code 09 or 65 or 89, for example. So we only would like to compare how good is the model simulating these stages. Then, like in the usual model, we define the phase sequence. And on top of this phase sequence, we also need to define calibration parameters. So we need to define a list of parameters that we tell the optimization algorithm to optimize. Okay, so the phase sequence looks quite similar to the original model run when we already know all the parameters. However, there are slight differences. And the differences is that we leave basically the response function keywords and the accumulation keywords empty. So we not specifically tell the model to use a specific threshold model, we just leave them out. So for example, the rectified linear unit has a lower temperature threshold. So in the usual run, we need to describe the lower temperature threshold as a parameter here, but we leave this here out. And also for the accumulation keywords, we usually need to know what is the accumulation response function. So how long should be summed up the response value until the phase is finished. So we leave these out. And on the other hand, we define the calibration parameters. And this is basically a list of the parameters and the locations we would like to calibrate. So for example, here in the phase sequence, we have defined, in the phase sequence, we have defined a phase bud development, and we leave out here certain response function values and accumulation values. And here in the calibration parameter, we specifically say in the bud development phase, there is a response function parameter that is the lower threshold, and this should be calibrated. So at the end, the model, the calibration model knows that in the phenology phase, in the phenology phase for bud development, I need to calibrate the lower threshold. I also need to calibrate the growth rate, and I need to calibrate the accumulation threshold. So it's basically a list of all the parameters that we would like to calibrate. Okay, and then like with the normal model, we define now the calibration model, and this calibration model now digests the phenological phase sequence that we have defined, the evaluation dictionary with the observation data and how to measure the closeness of our simulations to the observations, the climate data, and the parameters we would like to calibrate. And then we can use this entity model and put it into the standard optimization algorithms, like, for example, the scikit-learn optimization method. And this then gives us the parameters that are most optimal for these observations and for this designed phenological model. Okay, so this is how it looks like then at the end. So we have now two inputs. We have the climate input and we have the phenological input. The phenological input is designed that you have like in each row you have a specific year, and in each column you have the different BBCH stage, and then you have here the day of the year in this specific year where this BBCH stage was observed. So for example, the year 2000, BBCH stage 61 was observed on the day 157. So this is the input. that we need. On top, we need, of course, our metric to know how to estimate the closeness of our simulations to the observation. This is put into our evaluation dictionary together with the observed phenology. Then we put this into the calibration model, and what we get out of is when we optimize the optimized calibrated parameters. And here you see just one illustrative example of how this calibration works. So here we have the simulated day of the year for a specific BBCH stage. Here we have for different colors for bud break, leaf development, flowering, fruit development, and ripening. And on the y-axis, we have the observed day of the year, and you can see that the calibration works quite fine. So we are close to the 1-1 line here. So the model, the calibrated model is quite close to the observation. Okay, so this is how the model functions and how you execute the model and the calibration. And now I will finish the presentation with some sensitivity studies of this model and also with some projections of the future phenological development for Montenegro. And this is the basic setup that I tested here. I tested the model for 2 different sites. One site in Germany, which has the advantage that we have there 66 years observed phenology. So we have quite a long time series of phenological observations. And the other time series that I used is from Montenegro. And this is a much shorter time series. So we just started the observations in 2023. However, we have here 5 vineyards, and we basically squeeze all the vineyards into one giant time series, just for convenience. So these are the 2 sites that I would like to test. So just to see how well the model operates in different regions, or if there's some specific region that is not very well simulated by the model. Then with the phenological modeling framework, I tried to simulate 5 different phases, consecutive phases. So I would like to simulate the bud break, then followed by the bud break, the leaf development, then the flower development, fruit development, and the berry ripening. So these are the 5 phases I would like to simulate for both sites. What I did from the pool of 17 different response functions, I tested here 12 different response functions. And since I don't know the threshold parameters for these response functions for both sites, I calibrate them. And for the calibration, I use a quite simple and naive approach. I use the Nelder-Mead simplex optimization algorithm to determine the calibration parameter, the threshold parameters. And one difference to what is usually done in this calibration procedure, usually what you do when calibrating a complex phenological model that simulates separate phenological phases, you start by calibrating the phase for the bud development. Then you take the calibrated model for bud development and use it to calibrate the model for leaf development. Then you have a model that has a calibrated bud development and leaf development. And then you calibrate your model for the flower development and so on. So you calibrate them in a consecutive order. However, in this case, I try to test what happens if you don't make this sequential calibration, but calibrate everything together. So the model tries to calibrate the bud break development together with the flower development, together with the leaf development, and so on. The idea behind this was that in general, it could be, just coming from the machine learning background, that even though you simulated a bud development, so the very first development phase is maybe not calibrated that well, but still the later development stages might be better simulated with this bad development. So that was just the idea in mind that from first view, you should not assume that a good bud development will also represent then a good ripening development. And this is also an observation that Luisa showed, that there are specific thresholds in her model that are specific phases that are not modeled very well in her model, but the phase after the bad calibrated phase is still quite good. So that's why I choose here this calibration approach. What are the sensitivity tests that I would like to go through? One is just run the models in the usual setup. So the usual setup you do with a phenological model is you choose one phenological response function for each phase. So you choose, for example, the Unifan model or the Richardson model, and you use this model to simulate each single phase with different parameters, of course, but for each phase, you have the same response function. So how well does this approach work? And then I go one step further, and I take the 12 different response functions that I tested and try to simulate all the different combinations that I can have simulating 5 different phenological phases. So at the end, I end up with basically 250,000 different combinations of response functions to simulate 5 consecutive phenological phases. So I just try to identify whether there is a specific combination of models that works better, or a specific model combination that totally or creates totally junk, for example. And then I would like to show or simulate, or not simulate, I try to perform a sensitivity study that is important when we go to future climate projections, so the impact of climate change. I would like to test how well do the models actually are able to project future phenological development. So because we calibrate the models now, so under the climate conditions we observe now outside, we do not observe outside a 6-degree world, what is anticipated in the year 2100. So the question is, do these models also work properly in a 6-degree world? Or should we make some adaptations for the model? Or should we choose specific response functions because they are more able to operate in these hotter climate conditions than other response functions? So this is the third risk sensitivity test. Okay, so then what are the results of these sensitivity tests? Here you can see the first sensitivity test. So trying a homogeneous model setup, so using just one response function to simulate every of these 5 phases. And on the left-hand side, you can see the results for the German region, and on the right-hand side, you can see the results for Montenegro. And here we have, with the letters, each single response function. So in the upper row, we have the simple single threshold response function. In the middle, we have the more complex multi-threshold response function. And here down, we have the complex sub-daily response function, or the response function that considers sub-daily development. And you can see if we use homogeneous models, there is quite a large difference between the different response functions that we can use. In general, it looks like the single response functions operate quite good if they are simple enough somehow. So if we have, for example, A is a sigmoid, quite simple model. E and D are also quite good, or quite close to the to the observations. These are the rectified linear unit or the Réaumur model, and the parameterized exponential linear unit. So they operate quite well. If we go to the multi-threshold models, there is some deviation. And for the more complex models, like for example, the EPSIM model, you can see, and also for the Wang model, there's quite some difference for the observations. For example, for the Wang model, this model, if you use it in a consecutive order and simulate each phenological phase with this single model, for this site, the model cannot simulate the ripening. So it ends before the ripening period just starts. So it's quite bad. And it's nothing that I would anticipate. And the question is whether the simple calibration method that I used is here suitable. Comparing the German site and the Montenegro site, we can see that we have similar observations. So the simple models seems to operate quite well, and it gets difficult when we choose more complex models. Yeah. Then making the simulations with testing all the different combinations of response functions to simulating each phase. What I plot here is on the left-hand side, again, the German side, on the right-hand side, the Montenegrin side, and on the y-axis, we have the different models, the different response functions. And on the y-axis, I plotted the root mean square error distribution for this response function. So, and the root mean square error for the full model. So I have modeled with every combination the full phenological cycle. I calculate at the end over all the phenological cycle a root mean square. And then I can select all the models that have any weights always think for the Réaumur model inside. Then all the models that have the parameterized exponential linear unit inside to simulate some phase. And then I can decide at the end or see at the end which model is in general better to simulate or should be at least incorporated in a full phenological model, because on average, it has the best simulation results, no matter in which phase it is used to simulate phenological development. One observation you can see here is that the plots between the Montenegrin side and the German side are not so different. So we have quite a good agreement or similarity between both sides. So it seems the results does not matter from the observational inputs. So if you have more data or less data to validate, the results seems to be quite similar. Then in general, the best operating response functions seems to be these two here, the Gride and the Pelu, and also the most complex function seems to appear often in models that perform quite good. So this should be the choice, or you can think of that if you would like to build a phenological model for simulating your vineyard. The best choice might be to use these complex models or these more simple models. One observation that struggled me are the difference between the Richardson model and the Uniphen model. And you not recognize or remember, but these two models are quite similar. The only difference between the Richardson model and the uniform model is that the uniform model has one additional threshold. So intuitively thinking, they should end up at similar performances. But here you can see these models are quite different. Here in Montenegro, not so much, but wait. No, here they're quite different. So in Germany, not so much, but especially in Montenegro, they are significantly or have significantly different performance. And the only explanation I can give is that maybe the calibration method that I used, which is a simple Nelder-Mead method, might not be so suitable to calibrate complexer models, which has more parameters or strange functional forms. Then I can also analyze the results in terms of how good do each specific response function simulate a specific phenological phase. So therefore, I calculated the average root mean square for every model that has in the butt break phase, for example, the sigmoid function. Okay, so this is, for example, here on average, the sigmoid, a model that has a sigmoid function in the butt break phase will end up here. If the sigmoid function is in the leaf development, it ends here, and so on. So I can identify basically models or response functions that can better simulate a specific phase if they are orchestrated with all the others, all the other response function. And in general, we see a similar observation like in the plot before. So the simple models, the degree day, the PELU, and also the complex EPSIM and SING model end up in general having a good performance for every phase. However, if we try to use these functions for the ripening period, they end up quite similar. So choosing different response functions makes a difference for simulating the earlier development stages, but for the later development stages, it seems like the choice of response function is not so different. And then I can also use, I mean, I have simulated now 250,000 different combination of response functions, and I have seen in these in the analysis before that there are certain response function types that seems to simulate better and others simulate worse. The question is, what is at the end the best performance, the best model combination that we can have? And surprisingly, these are the results that I end up with. So this is really the two models, one for the German side, one for the Montenegro side, with a specific combination of response functions that really perform the best for these sites. And surprisingly, it's always a combination of the very simple models. So the complex models does not seem to improve in general the overall performance. I can build a phenological model just by choosing a suitable combination of simple models. So basically it tells you don't need the complex models, just choose the simple models and combine them in a wise way, and you end up with a total phenological model that simulates the full cycle in much better performance than using very, very complex models. And the results we have, at least considering the total phenological cycle, are quite good. So we have our square values close to 1, which would be a perfect match. So the take-home message here is the combination of response function matters and not so much the type of response function. And the simple methods seem to outperform the complex models if they are combined in a suitable way. Okay, then the last sensitivity study that I have did, I don't know how much time I have it, -5 minutes or so. Okay, let me be quick. So the question here was, how good do the models simulate the future? And there's a simple test or experiment that you can perform. I can do the calibration of these homogeneous models. So I take just models that simulate every phenological phase with just one response function. And for the calibration, I present the models only the cold years. Okay, so I select only years that are cold, and then I validate the models for the years that are hotter. So it's like, because, yeah, it's like the future. In the future, it will get hotter, but in my observations right now, I used to calibrate, I don't have these hot years because they are not observed. So basically, it's the same concept. I choose the cold years to calibrate the model and validate then the model on the higher temperatures. And then I can plot here what is the deviation between the model simulation with respect to the temperature anomaly of this year. So here on the x-axis, you always have the temperature values. So on the right-hand side is always the hotter years, and on the left-hand side, we have the colder years. And each plot here represents one response function. Then I plotted here the linear regression line for each phenological phase that I evaluated here. And you can, I just named here to interpret or how to interpret this plot. So if you have a plot with a line that has a positive trend, it means that in the future, this model will overestimate climate change impact. And if it's a negative line or has a line with a negative trend, then it will underestimate the climate change. And what you can see is that especially most of the simple models does not capture well the climate change. So despite the fact that these models have in total a better performance, if you combine them wisely, they might give you fault results if you would like to use them in climate change impact analysis. So they either, for example, the sigmoid model strongly overestimates the climate change. So the advancement of the phenological development to earlier dates of the year is much stronger with models using sigmoid response functions. And there are only a few models and phases, like, for example, now come back the complex functions, like the Epsom model or the Wang model, that seem to don't have this property. So they have a flat line, so they don't over or underestimate climate change impact. Okay, so now I would like to end the presentation with future projections for phenological development for Montenegro. And this is the setup that I used. So again, I used observations from Montenegro, and I used observations here from 5 different vineyards, from Kruna, Book, Plantage, Vucinic, and Rajkovic, sorry. So for these 5 sites, I have phenological observation, and I use specific climate data as at high spatial resolution, and I tested them for 2 different scenarios, or projected for 2 different scenarios. So I basically took, for the phenological development, I took the best model that I have identified from the sensitivity study. And one word of caution in the interpretation of these results, I have calibrated the model using 5 different vineyards, and the projections that I present is for the whole Montenegrin area, not taking into account that there are certain areas where there's no vineyard. So this is just, so to say, potential development for every grid point in Montenegro. And these are the results here. In the upper panel, we have the green future emission scenario, and in the bottom panel, we have the high emission scenario. And in each column, we have what is the change in the occurrence of bud break, what is the change in days, and the occurrence of flowering, of full fruit, and the ripening period. And what you can see is that there's in general an advancement of the phenological development. So the phenological development of each phase will become earlier, which is quite naturally because it gets warmer. But the accumulation of heat that the plant needs to fulfill a specific phenological development cycle is the same. So warmer means we have an advancement. The flowering seems to have, in both scenarios, will have the strongest increase. And right. So if you search now what is the actual date when ripening or flower development will happen, is that due to the advancement of the phenological phases, you end up with the observations that these two will happen in much hotter annual conditions. So you not just have the property that you have in general temperature increase, but also due to the advancement, the development will happen in times of the year that are in general hotter. Like the ripening will not happen in autumn, but happen in summer. So that will additionally accelerate the phenological development. Okay, and then last, you can also look how does the length of each phenological phase change. And this is for the bud break phase or the sprouting phase, the leaf development phase, flowering phase, and ripening phase, and how the full phenological development cycle from sprouting to ripening, end of ripening change. And one interesting observation is that the leaf development phase does not seem to have a strong change. So we have a shortage of the bud break phase and all the other phases. The flowering phase again will have the strongest shortening, but the leaf development phase does not seem to be affected strongly by climate change. So the leaf development phase is quite similar to what is observed right now. Okay, and I will spare the summary because I'm just a couple of minutes behind. Okay, good, thanks. That's all.
Thank you, Christoph, for your thorough presentation. And now I think we can head on to questions. Does anybody have any questions regarding, okay, here.
Hello, everyone. My name is Luca. First of all, thank you, Christoph, for the presentation. And since I am not a modeling expert, I have one very simple question. That's what is the correlation between variables that is sufficient in order to develop a good prediction model?
I don't know. Simple answer. So I haven't tested the correlations of the different, but of the different parameters with respect to the BBCH stage. But you can be sure that temperature has the highest correlation. Otherwise, these models would make sense.
I'm asking in general for modeling, not for the phenology, just in general.
Speaking of crop modeling,
Yes.
or So usually the mostly used variable in crop modeling is temperature. So temperature has the highest impact on most of the sub-processes that are simulated in crop modeling. So temperature really is the most important variable.
Thank you.
Are there any further questions?
Thank you, Christoph, for your very useful and detailed presentation. I have one very short question. How difficult is it to adapt model like this to another plant species? This is related to calibration and parameters only.
It is not difficult at all. All you need is an observation time series with the BBCH stage of this plant. And then you can just use it like here. So the only difference is the input. And maybe if you have a specific plant that don't have the inflorescence development, for example, then you need to adapt your phase sequence. But that's also straightforward. So you don't need to make any changes in the code. You just need to orchestrate the model a little bit different, and you need these observed inputs.
Okay, thank you.
And if we're done with questions, I think, thank you, Krista, very much for your presentation once again. I think we can wrap up the day with our final speakers actually, Vasily Mirovic and Danilo Salovic from Plantage. With their presentation, Climate Changes, Effects on Montenegro and Viticulture, a Plantage case study.
Okay, I will start because we are coming from the company Trinity Plantage, which is enterprise, one of the biggest enterprise for the production of grape wines and wines in region, not only in Montenegro. And I would like just to briefly represent our company and some of the history of the grape wine and wine production in Montenegro. So in the 1960s, the story about modern grape wine production and wine production started in Montenegro with a group of enthusiastic and visionaries who started the project. In that time, very ambitious, and it was a very ambitious project worth even 62 millions of American dollars, which was founded by the FAO. And in that time, they started the plantation of more than 2,000 of hectares of grape vines. So in that time, it was very ambitious and one of the biggest venture in viticultural production, even in Europe. But today, it's a very long story about the recognition and plantation wines. Today, it's Plantage cover around 2,300 hectares with around 11 millions of grape vines, different grape vines, mostly autochthonous grape vine varieties, Vranac, Kratošija, Žižek, Krstač, but also another introduced international grape vine varieties. So regarding when we speak about climate change, so just to have a short overview about the climate and the soil structure of the Plantage vineyards. So Plantage vineyards are bordered with very nature-influenced factors, just 30 kilometers from the Adriatic Sea, near to Lake Skadar, from one bordered with the Cievna Canyon River. Also from the other side, high altitudes of mountains. So that all makes Plantage vineyards very good in favor of the for the viticultural production and very good in the context of the climate. So Plantage vineyards are situated around 45 to 60 meters under the ground. And yeah, the layer, it's a plateau under the underwater waters, with also climate. When we speak about climate, it's with very high temperature during the summer months, or with the vegetation, and in the recent year, as we are all witness, very mild temperatures, and we will see how that's later influence on our vineyards and the quality of our grapes and wine. So regarding to the precipitation, regarding to the temperatures, we have 2,500 hours of sunshine annually in Plantage vineyards. So during the vegetation period, we always have more than 12 hours per day. The precipitation is around 1,600 liters. Sorry. So when we speak about the soil, as you can see, when the group of enthusiasts and visionaries planted Plantage, it was more the land with skeletal, with stone, than on the soil. Yes, definitely it's a 95% of the conglomerate of the stones, but only 5% of the fine soil. As I already said, the amount of the participation is around 1,600 milliliters of water residue annually, and the production of grape wine is not possible, as you know, without the water. So without the irrigation. So we have 23 wells all around the 2,300 hectares. But as you will see, we have indeed a lot of problems with water, with this water resource, because even though in these months, in June this year, few days ago, we have a problem that one of our wells have draw up. So although the FAO argued in the late 1980s that we will never have the problem with water scarcity, we definitely have it, because today we are witness of these, limited resources of water under our vineyard. So just briefly, the Plantage vineyards are mostly covered by Plantage varieties are mostly covered by Vranac variety, which is national proud, and almost 80% of the production is covered by Vranac. Also, as already said, we have other varieties like Kratošija, Krstač, Žižak, which are the autochthonous wine, and also the international wine, where we, in the sense of this climate change, also trying to see what kind of varieties are good adopted in our climate condition, and what kind of these varieties will have the highest yield, the highest level of the highest level of the wine as well. Not only that we have those varieties, we have also the stone production. I mean, the production of the table wines, it's around 10%. 70% are red wines, and we are famous by the red wines, as all Montenegro is. 20% are white wines. But I would also like to emphasize that beside of these very famous varieties, like a French wine, that we have Cabernet Sauvignon, Merlot, Chardonnay, etc. We also, in the context of these climate changes, We were working, but colleague will speak later on this topic. In finding the genetic resources of grapevines, which are very old, very well adapted on the climate change in Montenegro, very old, even some of them 50 to 100 years old. So regarding to the production, we have 3 cellars, one main cellar in Chemovsko Polje with a capacity of 30 millions of liters of wine, and the biggest production is over there. We have also two smaller wine cellars, Leško Polje and Šipčanik. Leško Polje is for the production of the premium wines, and Šipčanik is for the mostly as a touristic point, and also for the aging of very old wines. So when we speak about the climate changes, we are definitely the witness of the climate changes. I mean, we are all the climate changes affect all the production, affect the humanity. Even though I was recently involved in one project when we estimate the climate change influence on the gender equality, for example. I mean, everything is related to the climate change today. But definitely when we speak, this will be very soft comparing to the other presentation, I guess, and very, practical trend and found. When we speak about temperature regime and participation, it's very, very shift when we compare to 2 periods, and we were estimating the period from 1961 to 2000, and the period from 2007 until 2023. And what we found out that the temperature regime and the precipitation regime shift were very changed. We observed that the increase of the temperature, when you speak about the average annual temperature, it decreased 1.6 degrees Celsius degrees. And when we speak about, and you will see later, when we speak about the vegetation, it decreased also for 2 Celsius degrees. I have it on another slide. When we speak about precipitation, we have increase in the precipitation during the whole year. It's when we compare these 2 periods. When we compare to this 2-year period, it's increase in 6.5 percentages. However, we are facing with lower rainfall, lower precipitation during the vegetation period, when we need some of the rains, but mild rains. So when we need for our production, we don't have rain, and during the whole year we have a higher influence of the precipitation. What does it mean? That means that we have these last years and last even decades, we have higher temperatures followed by the very high rainfall. That influence on the overwintering of the different stages of the pests, different larvae. So the most important pests, like we have in our vineyard, Tulbesia botrana, for example, the green mold. So we have overwintering of this pest, and also as the climate change made a shift and moved earlier the vegetation period to start, we have from the very early beginning, we have the occurrence of the larvae and from the most important pest, which additionally influence on the protection products to be more implemented and the cost is also higher in the recent years as well. So this is basically what I was what I was saying. So we have the rise of the temperature during the whole year, but also directly the rise of the temperature during the growing season with lower precipitation during the vegetation and growing season. So all these things makes our production very difficult in last year. We will speak a little bit later on, I think now, about the extreme, what this also caused besides all the things that we already said. So these changes in the temperature regime and participation regime also we noticed we have as extreme. So in the last years we have a lot of extreme. So the mild temperatures during the winter period, high rainfalls, very high rainfalls, followed by the very long droughts and very long temperatures, makes our grapes more, dehydrated. So we have this. Okay, I have these photos. So it makes our grapes dehydrated. What does it mean? That means that we have a low sugar content, higher sugar content, low acidity content, which in the end appears that we don't have, the freshness, and we don't have that good ratio of the alcohol and sugar content, and also the freshness of the wines and what is the most important in wine production. Also, we have, because the temperature is higher during the nights, we have a very, tropical nights. We have a problem, especially with the white wines, because they need very cold summer nights, and because of the freshness of the wines and all alcoholic fermentation. So I will just return here just to mention that when we speak about extreme as well, there is no year in these 3-4 years, as I remember, that we didn't have hail. And we are just, looking at the sky when it's very hot, and suddenly the rain started. So we have a very huge problem. In 2022, we have, you can see on the left picture, we have a very high intensity of the hails, where the estimated damage from the hail in 2022 was around 8 million euros, which is, according to my memory, I think that I'm right, it was 30% of the whole production was destroyed. So you can imagine what kind of damage is that for the viticulture production. You can see on the rest on the both photos the damage from directly on the clusters on the berries as well. When we speak about the phenology, we noticed that the season started much more earlier. We started with the following of the phenological phases, mostly due to and thanks to the Montevitis project. Also, and we notice that there is a high shift, and a lot of days earlier, even 7 days per every phases it started. And also, what does it mean? That means that, for example, last year in 2024, we have a harvest of the vranac in August, which never happened. And what does it mean for the production company? That means that in that time, it's a high, Vranac was always picking up at in September. So when we started to pick up Vranac in August, there is a lot of additional problem. I mean, we have a high sugar content. We have also the labor. We have the labor problem. I mean, because it's vineyard is open factories. So during these months, it was not easy to find, a labor. We have that's also one more problem when we speak about climate change that directly influence also on the. So I think I'm mostly past to all this. Yeah, the onset of vegetation has shifted at 7 to 10 days earlier compared to the much more earlier data. So mostly I pass all through this. So when we speak about what are we going to do? Yeah, of course, we as Plantage are from 50 years ago, but from 2011, Plantage recognized the importance of the implementation of the science and its research in agricultural production. And from 2011, we have conducting and we have a license for the conducting the research in the field of agriculture. So we started with projects in order to improve our production and make an innovation. But also in the context of the climate change, that there were a lot of efforts to at least to mitigate those impacts. In that sense, we were doing some very important projects, like, as I already mentioned, the introduction of the new varieties, new rootstock, which are resistant to the climate changes. Also, we are trying to find new varieties that are probably in the future we'll have some maybe a gene for resistance for these climate changes, for the drought, for the high temperatures. So because we found 51 different unique varieties on the territory of Montenegro. So we will continue our efforts and our research in that direction. Also, we are doing some more smart techniques like, sensors for the irrigation and etc. So started from the pruning techniques that we are going to adapt to new era of the climate changes, to the most innovative. We are trying to do as much as possible in our company. So I will let to the floor my colleague, Danila.
In the context of the climate change marked by prolonged droughts and extreme temperatures, an advanced irrigation system is one of our most critical solutions. Across 161 hectares of newly established vineyard, we are currently implementing a comprehensive smart drip irrigation system with sensor, automated wells, and remote control. This system enables not only even and targeted water distribution, but also real-time drought monitoring through soil moisture sensor, leaf wetness sensor, and an integrated weather station network. The built-in fertigation unit allows precise nutrient dosing through the irrigation system, further enhancing efficiency and adaptability to changing climatic conditions. This system is a strategic investment over more resilient and sustainable viticulture. Now, PV varieties represent one of the most promising solutions for viticulture in the face of the climate change. and the need to reduce chemical treatments in 2024, Plantage initiated experimental plantings with several PV varieties, including Borner, Muscarius, Sauvignon Gris, Prior, and Cabernet Cortis. These varieties, developed by German and French research institutes, are already established in EU vineyard. They are strong resistant to fungal disease, allow for a drastic reduction in fungicides, making them ideal for organic production. Fewer treatment also mean less soil compaction, preserved biodiversity, and a lower carbon footprint. While trials are ongoing, early results show potential for early ripening, high yields, and constant quality. The critical traits is increasingly extreme weather conditions. Precision viticulture is an approach that uses technology to view a vineyard not as a single uniform unit, but as a mosaic of microzones, each with its own specific need. From a technological standpoint, this includes tools such as drones, GPS, weather stations, soil moisture sensors, NDVI satellite imagery, and specialized software. The goal is not just to automate work, but to intelligently adapt agronomic practice to specific conditions. For example, avoiding blanket pesticide application if disease symptoms appear only in certain zones. This approach enables high yield and quality because each vine gets exactly what it needs, lower cost by eliminating reservoir waste and unnecessary areas. Eco-sustainability crucial for both market demands and regulation today. At Plantage, we took a major step toward precision viticulture by introducing multispectral drone technology late last year. We are currently in the research and experimental phase, capturing images of selected linear parcels at a different growth stage, building an internal database for future reference. So far, flights have been conducted while vegetation was still relatively sparse, ideal for familiarizing ourselves with the platform, flight operation software, and operational protocols. Through analytic insight, example detecting intraparcel variability will emerge the coming weeks as the vegetation reach full intensity. This is when NDVI and other indicates the best reflect of fine health variation. Though it's still early for conclusion, we already see the potential for scaling the system, especially when integrated with the weather station GIS. Right now, we are focused on data collection and mastering the technology, but the preliminary results are promising. This groundwork let us envision how the system will operate at full capacity, leading us to the next slide. Here we represent the vision that integrates all technology, from imaging and analyzing the real-world application. This example illustrates how digital vine protection tools soon become faster, early detection via drones, more precise target treatment, don't blanket spraying, more efficient, lower cost, fewer chemicals, and better environmental protection. How it works in practice. A multispectral drone scans 10 hectares on vineyard. AI analyzes NDVI data and flags a 2 hectare stress zone. Field technician inspect and confirm that early stage downy mildew. A precision spray drone treats only the affected area, not the entire vineyard. Key benefits of this is cost saving, up to 80% less pesticide use versus blanket spraying, environmental protection, minimize chemical runoff, faster response, early detection, prevent disease spread, and higher efficiency, optimize resource allocation. This is one of our key strategic goals for the upcoming season. As a part of our precision viticulture system, we are currently using 2 types of weather station. The first is the AgroNet station, which continuously measures key microclimatic parameters, air temperature and relative humidity, soil moisture contact, leaf wetness, which is particularly important for assigning the infection potential of fungal disease, as well as the wind speed and direction. The second is at-field station, currently in the testing phase. The main advantage of this platform is the ability to predict disease and pests based on local weather condition and epidemiological models. Together, these 2 stations will provide the foundation for integration with drone imagery and decision-making regarding interventions. We are also in the process of procuring smart digital traps from the agronet system, which automatically detect and count pests and include additional sensor for temperature and air humidity. This trap will be integrated into the same platform, giving us even more detailed insight into pest pressure, such as grapevine moths, and enabling a fully connected system from weather and entomological monitoring and then NDVI analyze and precision plant protection. This slide addresses one of the key aspects of adapting viticulture to climate change: the preservation and valorization of genetic diversity of indigenous grapevine varieties. Genetic diversity is not just scientific category. It directly enhances the vine resilience and climate stressor, including droughts, extreme temperatures, and increasingly frequent disease. Additionally, a diverse genotype base enables the selection and realization of local varieties that have historical proven most resilient to Montenegro specific agroecological conditions. This multi-year project conducted in collaboration with the Spanish Institute of Grapevine and Vine, ICVV La Rioja, analyzed over 500 samples, including 101 cultivated and 43 wild grapes genotypes. To date, 50 varieties have been identified, while 51 cultivars remain unidentified. Project confirming Montenegro's rich yet still underexplored genetic heritage. A key outcome is the establishment of a national collection of indigenous grapevine varieties, such as portfolio, serving as foundation for conserving genetic resources and future breeding programs. Moving forward, these findings will enable the selection of drought and heat-resistant varieties and development of new clonal lines. This project's validity has been further reinforced by publication in scientific reports, adding international credibility to this research. Clonal selection advantage represent one of the most complex yet critical processes for long-term climate adaptation. Since 2004, this project has been focused on ranac, Montenegro's most important variety and genetically valuable resource. Selection criteria included yield potential, plant health, chemical composition of berries and vine. After years of analysis, ampelography, microunification, sensor evaluation, 7 ranac clones were certified. Key traits of selected clones is balanced sugar acid ratio, vital for climate resilience, higher phenolical and antioxidants, improved vine quality, stable yield even in drought years, preserved aromatic complexity. Concurrently, modern vineyards were established to produce certified disease-free planting material, ensuring genetic purity while preparing viticulture for climate challenges. This initiative not only enhances our production but actively safeguards varietal integrity and keeps vineyard for future conditions. In the context of climate change and growing demands for reduced chemical inputs, biostimulants and eco-friendly solutions play a key role in the transition to sustainable viticulture. Biostimulants are not only replacement for pesticides, either they naturally enhance the plant's stress tolerance, boost its immune response, and improve nutrient efficiency. Their application reduces synthetic inputs, minimizing pollution while preserving soil health and beneficial organisms. At Plantage, we invented trials with 2 formulas in Cemovsko vineyard as a part of the Trace Video and Smart project. Trace Video is an international project advancing the vine traceability and now technically while promoting sustainable viticulture through biostimulant use. At Plantage, trials in 2023 and 2024 compared treatments, including fungicide-free biostimulant application. Results show biostimulants reduce botrytis infection, maintain yield, and enhance vine composition. anthocyans, and polyphenols without compromising quality. Sensory analysis confirmed these wines meet high standards, providing biostimulants are a viable tool for climate resilient, low pesticides viticulture. And now, PhytoSmart. PhytoSmart is an ecological product with remarkable physiological effects of vines. Unlike traditional treatments, it works by enhancing plant metabolism, improving leaf hydration, and reducing water loss, critical for climate resilience. Our 2023 trials on walnuts and cardinals showed clear benefits, boosted photosynthesis, thicker skin, stronger disease resistance, and stable yield. Notably, vines required a few fungicides, and they maintained physiological stability, even under the stress. PhytoSmart exemplifies how innovative plant nutrition technologicals can become key allies in sustainable chemical-free viticulture. Systematic phenological monitoring is the key tool for understanding how different grape varieties behave under our agroecological condition. Using BBCH scale, a universal language for wine development, we track growth range across multiple sites, including a national collection, international varieties, PV trials, and runoff clones. This method is also integrated in the experiments like Trace Video and PhytoSmart, where we study whether biostimulants affect the growing tempo, ripening for stress resilient at specific phenological stage. So, thank you for your attention. If you have any questions.
Are there any questions? No questions? So see online, if you have any questions? I think we don't have any questions online. So thank you for your presentation, very interesting presentation. I can pass the word for Michael, maybe to finish. Closing words today. Okay. Kruna.
Yes, hello to everybody. So thank you for following the second day of the summer school. Hopefully we have one remaining day, and I hope that the lectures will be also as interesting as for today's meeting. And I wish you all a nice afternoon and see you tomorrow morning. Thank you. Thank you. Thank you for the people online as well. Thank you so much.